What if I told you there's a kind of explosion so powerful, so unfathomably intense, that it could make a supernova look like a candle flickering in a storm? An event so extreme it blurs the line between science fiction and reality? A transformation where even the dense remains of a dead star collapse not into a black hole, but into something far more exotic, a realm governed by the deepest laws of particle physics. That phenomenon, hidden in the vast tapestry of our universe, is called a Quark Nova. But before we continue, subscribe to the channel. For centuries, humanity has stared into the night sky, awed by the brilliant deaths of stars. Supernovae, those cosmic fireworks, have lit up galaxies and sculpted the elements that make up our bodies, our planets, and our very breath. Yet, in the shadows of these well-understood titans of stellar death lies a more enigmatic force. A theory so bold that it challenges the very way we think about matter, mass, and the evolution of the universe. The Quark Nova is not a fantasy. It's a frontier, an edge where known physics meets the unimaginable. Imagine a neutron star, already the densest known object in the universe outside a black hole. A stellar remnant so compact that a single teaspoon of its matter would weigh billions of tons. But what if even that wasn't the final form? What if the core of that neutron star, under the crushing weight of gravity and quantum pressure, reached a tipping point, a phase transition not just in density, but in the very identity of matter? This is the Quark Nova. A second explosion, a delayed detonation triggered after the supernova. It's a theoretical possibility, yes, but one grounded in the hard mathematics of quantum chromodynamics and dense nuclear matter. In this colossal event, the neutrons in the star implode into their most elementary constituents, quarks. The building blocks of protons and neutrons themselves, quarks, become free, forming what is known as quark matter, or more precisely, strange quark matter, a state theorized to be even more stable than normal nuclear matter. And in this act, an entirely new kind of object is born, a quark star. The birth of a quark star through a quark nova is not gentle. It is cataclysmic. The transition releases an immense amount of energy, potentially up to 10 to the power of 53 ergs, rivaling or even exceeding the energy output of the original supernova. But it's not just the raw power that captivates astrophysicists. It's the implications. A quark nova could be responsible for the most mysterious gamma-ray bursts, the ultra-high-energy cosmic rays that batter Earth from distant galaxies, and perhaps even the elusive origin of dark matter or dark energy. It could be the hidden trigger behind certain superluminous supernovae whose brightness has puzzled scientists for decades. To begin to understand a quark nova, we must first journey through the life of a massive star. We must climb into the heart of a stellar furnace, follow its collapse, its death, and its rebirth as a neutron star. Then, with patience and precision, we must wait, for days, weeks, or even years, as the neutron star reaches its threshold. Its quarks begin to stir, no longer content in their neutronic prisons. And then, boom! A second detonation. A quantum inferno. Let's start with the life of the progenitor, the massive star that sets everything in motion. Stars of high mass, say, 8 times the mass of our Sun or greater, spend millions of years fusing hydrogen into helium, and then helium into heavier and heavier elements. This fusion provides the outward pressure that keeps the star stable, resisting the inexorable pull of gravity. But this can't go on forever. Iron is the end of the line. When a star's core is primarily iron, fusion stops being energetically favorable. The balancing act is over. Gravity wins. The core collapses in milliseconds. The outer layers crash inward and rebound, triggering a supernova explosion. What's left behind, if the star was just the right mass, is a neutron star. And these are no ordinary objects. Neutron stars are so dense, so tightly packed, that they challenge our intuition. A neutron star packs a solar mass into a sphere barely 20 kilometers across. Its gravity is intense enough to bend light around its surface. Its magnetic fields can be trillions of times stronger than Earth's. Its surface is a crust of neutron-rich nuclei, floating above a liquid sea of neutrons. And at the core, possibly, quark matter. But not all neutron stars are stable. If they accrete more mass, or cool over time, or spin down, the core density may rise above a critical threshold. According to some theoretical models, this is where the neutron star enters a metastable phase. It is not yet a quark star, but it is no longer safely a neutron star either. It's on the verge, teetering on a subatomic knife's edge. Here, deep in the heart of the star, the pressure becomes so immense that quarks, once confined within neutrons, are liberated. This process is called deconfinement. The neutrons disintegrate into up, down, and strange quarks, forming a quark-gluon plasma, a state that hasn't existed naturally since microseconds after the Big Bang. The conversion front, where this transformation happens, sweeps outward like a detonation wave. It's not an ordinary shock wave. It's a quantum phase transition front. And behind it, the star is no longer the same. The outer layers of the neutron star, unable to withstand the sudden change in core properties, are blown outward in a violent explosion. This is the Quark Nova. The energy released is astronomical, potentially dwarfing the original supernova. The ejecta, now traveling at relativistic speeds, can collide with the older supernova remnants, creating shockwaves and light echoes that astronomers might observe as unusual supernova rebrightenings or mysterious gamma-ray bursts. What's left behind is a quark star, a hypothetical type of compact star made entirely of strange quark matter. These stars, smaller and denser than neutron stars, may spin incredibly fast and emit exotic forms of radiation. Some models suggest quark stars could be stable for millions or billions of years. Others posit they may decay or convert nearby matter into strange quark matter, growing like a subatomic infection in the cosmos. The physics that governs all this is the domain of quantum chromodynamics, the theory of the strong nuclear force, which binds quarks together inside nucleons. Unlike electromagnetism or gravity, the strong force has peculiar properties. It gets weaker at short distances, a phenomenon called asymptotic freedom, and stronger at large distances, making it impossible to isolate a single quark. But in the heart of a neutron star, where pressures are unimaginable, this barrier may be overcome. Quarks may finally be freed, not into isolation, but into a new collective state. A soup of strangeness. And yet, despite the elegance of the theory, we've never directly observed a Quark Nova. Its signatures are elusive, possibly hidden within the noise of other astrophysical phenomena. But scientists are watching. Radio telescopes, X-ray observatories, gravitational wave detectors, they all seek the telltale signs. A delayed gamma-ray burst. A sudden rebrightening of a known supernova. A neutron star that vanishes without forming a black hole. A whisper in the cosmic dark. The implications go beyond stellar death. If quark matter is the true ground state of matter, as some hypotheses suggest, then the universe could be filled with strangelets, tiny pieces of quark matter drifting through space. These particles might catalyze the conversion of ordinary matter into strange matter, like sparks igniting dry grass. Some even speculate that a single strangelet hitting Earth could trigger a runaway reaction, though such scenarios, while terrifying, are considered extremely unlikely. Still, the study of Quark Novae is not just a curiosity. It is a journey into the most extreme physics nature can provide. It challenges our understanding of matter, of stellar evolution, and of the ultimate fate of the cosmos. As we refine our models and build more sensitive instruments, we may soon detect the first true Quark Nova. And when we do, it will open a new chapter in astrophysics. One where the smallest particles collide with the largest structures. One where the death of a star gives birth not to silence, but to something far stranger. And so the mystery deepens. The night sky holds its secrets close, but we are learning to listen. To decode the whispers of quark matter, to see beyond the visible, to understand the universe not just as it is, but as it might be. In the coming hours, we will explore every dimension of this topic, its theory, its implications, its controversies, and its cosmic consequences. From the quantum foam to the death of stars, from particle accelerators to distant galaxies, the Quark Nova links them all. The story is just beginning. As we continue unraveling the tale of the Quark Nova, let us venture further into the labyrinth of high-density astrophysics, where the boundary between established science and speculative frontiers becomes delightfully blurred. One of the most compelling aspects of this phenomenon lies in its theoretical framework. What allows a neutron star to become a quark star, and what defines that precise moment when it transitions from one state of matter to another? To comprehend this, we must journey even deeper into the dense core of a neutron star and examine the very fabric of matter itself. Neutrons, though often imagined as solid and indivisible, are in fact composed of three quarks, two down quarks and one up quark, held together by gluons, the carriers of the strong force. Under typical conditions, these quarks are forever confined within their nucleonic prison. But at the densities reached in the cores of neutron stars, several times the nuclear saturation density, the rules begin to break down. At such extreme pressures and temperatures, something extraordinary might occur: quark deconfinement. Here, the individual nucleons dissolve, and the quarks form a sea, a continuous, unbounded fluid of elementary particles. This is the quark-gluon plasma, a primordial state of matter that last existed moments after the Big Bang. In a Quark Nova scenario, this deconfinement doesn't happen as a slow transformation, it occurs in an explosive, runaway process. But how exactly does this transformation propagate through the neutron star? This is where things become exquisitely complex. The front of the transition wave moves outward through the star's interior in what can be described as either a deflagration or a detonation, depending on the model. In a deflagration, the front is subsonic and driven by thermal diffusion. In a detonation, it is supersonic and driven by shock. The precise nature of this wave determines the outcome of the event, how much energy is released, how quickly the conversion occurs, and what form the remnant will take. It's important to note that the conversion to quark matter may not proceed uniformly. Some theories suggest the formation of mixed phases, where quark matter and nuclear matter coexist in equilibrium over regions of the star. Others describe percolation phenomena, where bubbles of quark matter nucleate and grow, like boiling water, until they merge and engulf the entire core. The resulting energy release, driven by the pressure difference between the neutron and quark phases, can be staggering. The process is also profoundly asymmetric. Unlike a traditional supernova, where the explosion radiates spherically, a quark nova could emit highly anisotropic outflows, particularly if the original neutron star was rotating rapidly or had intense magnetic fields. These outflows, when interacting with surrounding matter, could generate relativistic jets, potentially explaining certain types of long-duration gamma-ray bursts, GRBs, that have puzzled astronomers. These gamma-ray bursts, among the most luminous electromagnetic events in the universe, have durations ranging from seconds to minutes and are followed by a gradually fading afterglow. The leading models for long GRBs include the collapsar model, where a massive star collapses into a black hole, and the magnetar model, where a highly magnetized neutron star powers the burst. But neither model can account for every observed GRB. The Quark Nova theory adds a fascinating alternative: a delayed detonation following the birth of a neutron star, where the initial supernova explosion is followed, days or weeks later, by a second explosion, the Quark Nova. This two-stage explosion would produce a rebrightening of the light curve and potentially launch additional material at nearly the speed of light. Indeed, observational data from certain superluminous supernovae, SLSNA, supernovae that are 10 to 100 times brighter than standard ones, have shown double-peak light curves, where a second brightening follows the initial explosion. These events could be prime candidates for Quark Novae. The first peak would correspond to the regular core collapse supernova. The second, brighter peak could be the result of a Quark Nova explosion re-energizing the expanding supernova ejecta. This idea is not without controversy. The astrophysics community is divided. Some researchers remain skeptical of the existence of stable strange quark matter, the essential ingredient in a quark nova. Others point out that the parameters required for such a conversion, mass, density, cooling rate, and magnetic field strength, must be finely tuned. Yet models of quark matter do not rule out its stability. In fact, the strange quark matter hypothesis posits that matter composed of up, down, and strange quarks in a certain ratio may be the true ground state of all matter, more stable than even atomic nuclei. If this is correct, then ordinary matter is only metastable, and quark matter is the ultimate endpoint of baryonic material. The implications are astonishing. A neutron star undergoing a phase transition to quark matter would not only explode, it might also trigger the conversion of neighboring matter. Any atomic nuclei that come into contact with strange matter might themselves transform into quark matter, a reaction that could, in theory, spread like a chain reaction. Some even suggest that a quark nova could seed the galaxy with strangelets, tiny fragments of strange quark matter that survive the explosion and drift through space, potentially converting anything they touch. While this doomsday scenario has captured the imagination of science fiction writers, reality is far less alarming. Strangelets, if they exist, are unlikely to be dangerous. High-energy collisions at particle accelerators such as the LHC have failed to produce them, and the universe itself is a vast arena of natural particle collisions far more energetic than anything we can replicate. If strangelets posed an existential risk, they would have likely wiped out entire solar systems by now. But they haven't. Still, the possibility of strangelets presents fascinating experimental opportunities. Could these tiny particles be detected in cosmic ray experiments? Could they be captured in ultra-sensitive detectors designed to spot exotic matter? Some experiments, like AMS-02 on the International Space Station, are already searching for anomalies in cosmic ray composition that could hint at the presence of strange quark matter. So far, the results are inconclusive, but the search continues. Meanwhile, theorists explore the equation of state, EOS, for dense matter, the mathematical relationship between pressure, density, and temperature in a star's core. Different equations of state yield dramatically different predictions. A stiff EOS implies a more massive and stable neutron star. A soft EOS allows for easier collapse or transformation. The discovery of ultramassive neutron stars, such as PSR J0740 plus 6620, with a mass over 2 solar masses, places constraints on the EOS and thereby on the possibility of a quark nova. Recent gravitational wave detections have added new data to the mix. The merger of 2 neutron stars, observed in 2017 as GW170817, not only produced gravitational waves but also emitted a kilonova and potentially a short gamma-ray burst. Could some of this ejecta have included quark matter? Could the resulting remnant have undergone a delayed quark nova? We don't yet know, but the question is tantalizing. We also must consider the magnetic field. Neutron stars often possess intense magnetic fields, sometimes exceeding 10 to the power of 15 Gauss in the case of magnetars. Such fields can affect particle behavior, alter the phase transition threshold, and channel the explosion asymmetrically. In fact, some models propose that magnetars might be protoquark stars, where the magnetic field and rotation rate are tied to the early stages of quark deconfinement. Rotational energy is also a key player. Young neutron stars spin rapidly, hundreds of times per second. As they spin down over time, centrifugal support diminishes, increasing the core density. This could act as a trigger for the quark nova, suggesting that spin-down rate could be a predictor of future explosions. A star could live for years or decades as a neutron star before suddenly detonating in a second burst of brilliance. Even the crust of the neutron star plays a role. The crust might delay the expansion of the quark core, trapping energy until it breaks open catastrophically. This delayed crust cracking could serve as the final, fatal straw in the conversion process. A neutron star's exterior, often considered inert, may thus become the stage for one of the universe's most dramatic metamorphoses. The more we learn, the more questions arise. Could Quark Novae be responsible for fast radio bursts, FRBs, those millisecond-long pulses of radio waves of unknown origin? Could they be linked to anomalous X-ray pulsars, or explain the rapid variability in X-ray transients? Could quark stars harbor exotic superconducting phases, or display color-flavor locking, a bizarre form of matter where quarks pair up like electrons in a superconductor? These are not idle speculations. They are grounded in the mathematics of quantum field theory, general relativity, and nuclear astrophysics. They point to a future where observational astronomy and high-energy physics converge, a future where the cosmos itself becomes our laboratory. But even now, buried deep in the catalogs of unexplained phenomena, there may be evidence waiting to be discovered. A Quark Nova could have already happened. It could be echoing across the galaxy, its afterglow hidden in data we've already collected but not yet understood. And so we watch. We wait. We listen. The story of the Quark Nova is not a myth. It is a hypothesis built on the edge of what we know and what we dream. In the vast, silent theater of the cosmos, it may be the next great act to unfold. The cosmic silence is deceptive. It is a silence that hides unimaginable violence, a silence that may, at any moment, be shattered by the explosion of a neutron star transforming into something even stranger. If a Quark Nova does occur, what would it look like to us, peering across the void with our telescopes and instruments? To recognize a Quark Nova, we must distinguish it from other cosmic cataclysms, supernovae, gamma-ray bursts, magnetar flares, and neutron star mergers. This is no simple task. Nature is not generous with clarity. But it is not silent either. The signatures of a Quark Nova may be subtle, but they would leave fingerprints, if we know where to look. One of the most promising candidates is the double-humped light curve. In several rare supernova observations, astronomers have recorded two distinct peaks in brightness. The first, relatively faint, corresponds to the Quark-collapsed supernova. But then, unexpectedly, a second, brighter peak follows days or even weeks later. According to Quark Nova models, this second peak represents the delayed detonation, the moment when the newly born neutron star becomes unstable and detonates into a quark star. This second explosion is not merely a burst of light. It re-energizes the outer supernova ejecta, heating it up from the inside like a glowing ember reigniting an already burnt log. The result is a superluminous event, far brighter than any typical supernova. If the delay between the explosions is just right, and the energy released sufficient, this renewed light show would glow intensely for weeks, a beacon in the deep night of space. But optical light is just one piece of the puzzle. A true Quark Nova would release radiation across the electromagnetic spectrum. In the high-energy range, X-rays and gamma rays, the detonation could produce an intense, sharp burst followed by a soft, fading tail. This signature could mimic a gamma-ray burst, particularly the subset of long-duration bursts. But the timing and decay profile would differ subtly, enough that, with careful analysis, astronomers could distinguish them. Moreover, the interaction between the Quark Nova ejecta and the original supernova shell would generate shock waves. These shock waves would heat the surrounding gas to millions of degrees, generating a secondary thermal X-ray glow. The light curve might exhibit plateaus, bumps, or sudden drops, depending on the density profile of the ejected material and the speed of the secondary explosion. At the heart of this astrophysical orchestra lies a powerful and deeply quantum process, the sudden liberation of energy from a dense sea of quarks. When neutrons dissolve and form a strange quark matter core, the binding energy of the new state may be lower than the combined mass of the original baryons. The difference is released, not as a gentle exhalation, but as an explosion, on the order of 10 to the power of 52 to 10 to the power of 53 ergs, rivaling the energy of a supernova or even a neutron star merger. This energy doesn't just disappear. Some of it is emitted as light and radiation. Some is converted into kinetic energy, propelling ejecta outward at relativistic speeds. And some might be carried away in the form of gravitational waves, ripples in the fabric of spacetime. Though these waves would be weaker than those produced by mergers, their unique frequency and duration could serve as a new kind of cosmic fingerprint. A distinctive, sharp spike in gravitational wave detectors, short, intense, and asymmetric, might betray the moment of quark deconfinement. We must also consider neutrinos, those elusive, nearly massless particles that flood the universe. In a quark-collapsed supernova, the majority of the energy is carried away by neutrinos, not light. A quark nova, too, would unleash a torrent of neutrinos, especially during the initial transition phase. If such an event occurred close enough, within our galaxy, neutrino observatories like Super Cameo Candy, Ice Cube, or Dune could capture the fleeting burst. The timing, intensity, and flavor composition of the neutrinos would differ from those seen in ordinary supernovae, offering another method of detection. Yet, the story doesn't end with photons and neutrinos. Matter itself would be altered. The outer layers of the neutron star, once composed of heavy nuclei and neutron-rich elements, would be blasted outward. This ejecta, enriched with neutrons and subjected to extreme temperatures and pressures, would become a fertile site for our process nucleosynthesis, the creation of the heaviest elements in the universe. Gold, platinum, uranium, all of these may owe their existence not just to neutron star mergers but also to quark novae. The second explosion could provide a second, more intense wave of neutron-rich material, enabling the creation of isotopes that cannot be produced in supernovae alone. If this is true, then the jewelry we wear and the fuel for nuclear reactors might trace their ancestry to a cosmic quark flash billions of years ago. Even more provocative is the possibility that quark novae are not rare. If they occur even in a small fraction of neutron stars, their cumulative effect over cosmic time could reshape our understanding of stellar evolution. They would represent a third endpoint, beyond white dwarfs and neutron stars, a bridge to the quark star. Quark stars, if they exist, would be smaller and denser than neutron stars. Their surface would not be made of atoms, but of bare quark matter, exotic, color charged, possibly in a superconducting or superfluid state. Light emitted from such a surface would be unusual, perhaps appearing dimmer or redder than expected due to strong gravitational redshift. The star's thermal emission might mimic that of a neutron star, yet detailed spectra could reveal hints of its exotic composition. Their rotation rates might differ. Their cooling curves would diverge. Their magnetic field structure could be radically different, perhaps twisted or even non-dipolar. All of these properties are testable, at least in principle. But the difficulty lies in the details. Neutron stars and quark stars may appear nearly identical to a distant observer. Only through meticulous comparison of multiple data sources, timing, spectrum, gravitational waves, neutrinos, could the truth emerge. And then there is the ultimate question: what happens after the quark nova? Does the star stabilize as a quark star, eternally bound in its exotic form? Or does it collapse further, crossing the event horizon and becoming a black hole? This depends critically on the mass of the remnant and the equation of state of quark matter. Some models predict a metastable quark star that persists for millions of years. Others suggest a delayed collapse, a quark nova that heralds not just one transformation, but two, with the second being the final, inescapable collapse into darkness. If a quark nova leads to black hole formation, it might emit one final cry, a blast of gamma rays, a cascade of neutrinos, a last ripple in spacetime, before vanishing forever. Such a triple transition object, a neutron star to quark star to black hole, would be a new class of stellar remnant, a life cycle we have never fully witnessed. And if these transitions can happen, then we must consider the next possibility: quark nova chains. Could a single explosion trigger others nearby? Could the ejected strangelets seed nearby neutron stars, transforming them in turn? A wave of quark transformation spreading through a dense star cluster is unlikely, but not impossible. It would be a cosmic domino effect, a chain of explosions lighting up a region of space like fireworks in slow motion. And beyond even that lie the most speculative frontiers. Some physicists suggest that the core of a quark star may collapse into preon matter, a hypothetical state composed of particles even smaller than quarks. Others propose that dark matter could accumulate in the cores of neutron stars, destabilizing them and triggering premature quark nova events. The fusion of exotic physics and astrophysical observations opens the door to discoveries we can hardly yet imagine. As we continue this journey, we must remain vigilant, not just for the dazzling explosions and brilliant afterglows, but for the subtle anomalies, the quiet deviations from expectation, the unexplained irregularities in our observations. In them may lie the truth that the universe is stranger, denser, and more explosive than we ever dared believe. One of the most tantalizing clues supporting the existence of Quark Novae lies in the handful of superluminous supernovae that defy traditional modeling. These outliers shine too brightly, for too long, and with strange spectral signatures that resist easy classification. They burn with the intensity of 100 billion suns, sometimes peaking in luminosity orders of magnitude above that of a standard Type II supernova. In these rare events, a simple core collapse model falls short. The energy budget is too high, the timeline too extended. This excess energy demands an additional source, and the Quark Nova scenario fits the requirement like a key in a cosmic lock. In the dual-shock Quark Nova model, a neutron star formed during the initial supernova remains temporarily stable. Then, days or weeks later, it undergoes a second catastrophic transformation into a quark star. The outer crust is ejected in the first explosion, and just as that material is cooling and expanding, the second explosion slams into it from within. This internal detonation acts like a second engine, injecting new energy into the original ejecta and reheating it to extreme levels. The result is a luminous resurgence, a second peak, and a spectrum that shows evidence of unusually high-velocity material and exotic chemical signatures. Among the candidate events, SN 2006 GY remains one of the most studied. Its brightness, longevity, and spectral features suggest a process far more powerful than standard supernovae can account for. While some posit apparent stability supernova as the cause, others argue that such an event cannot produce the observed time profile or chemical composition. A Quark Nova model, involving the delayed collapse of a neutron star into a quark star, matches the data more closely in some interpretations, particularly when taking into account the reshocked ejecta and the need for continuous energy injection. Theoretical modeling of Quark Novae requires complex equations of state that describe how matter behaves under unimaginable pressure. These equations must account for the behavior of up, down, and strange quarks, as well as gluons, which act as the mediators of the strong nuclear force. At such densities, the distinction between individual nucleons vanishes. Protons and neutrons dissolve into a sea of quark-gluon plasma, where quarks are no longer confined in trios but move freely among one another. This is not a gas, but a perfect fluid with nearly zero viscosity, according to lattice QCD simulations. A phase transition of this magnitude is not just a rearrangement of internal structure, it is a fundamental shift in the state of matter. One leading model, the MIT bag model, treats the transition as a change in vacuum energy between confined and deconfined phases. When the energy density crosses a critical threshold, the vacuum itself changes state, and the release of latent energy contributes to the explosive power of the Quark Nova. More advanced models like the Nambu-Jonah-Lacinio model include chiral symmetry restoration and incorporate the effects of color superconductivity, predicting that the core of a quark star could exist in a color-flavor locked phase where quarks pair up in a manner analogous to Cooper pairs in a superconductor. The physical characteristics of the ejecta are also unique. The outer layers of the neutron star are expelled at relativistic speeds, with some models predicting velocities up to 0.99 c. The mass of this ejecta is typically low, on the order of 10 to the power of -3 to 10 to the power of -2 solar masses, but its composition is exotic. It may contain hyperons, kaons, and even strangelets, hypothetical particles of stable strange quark matter. If strangelets are produced and survive, they could provide a signature unlike anything else in astrophysics. Some even speculate that if a strangelet were to make contact with ordinary matter, it could trigger a chain reaction converting normal matter into strange matter, although the consensus is that such a scenario is extremely unlikely due to charge and mass constraints. Quark novae also have implications for pulsar behavior. The transition from neutron star to quark star might be associated with sudden changes in spin frequency, magnetic field configuration, or emission pattern. Some observed pulsar glitches, sudden jumps in rotation speed, could be linked to internal phase transitions, possibly even the onset of deconfinement in the core. If a neutron star's core begins to form a quark matter bubble, the resulting pressure imbalance could alter the moment of inertia and cause a glitch. Observations of pulsars like the Vela and Crab pulsars show glitch patterns that might hint at more exotic internal physics than currently assumed. The birth of a quark star may also produce unusual magnetic phenomena. If the star retains a strong magnetic field from its neutron star progenitor, and if superconducting quark matter amplifies or reconfigures this field, the result could be a magnetar-like object with field strengths exceeding 10 to the power of 15 Gauss. These objects could emit intense X-rays and gamma rays, powered not by rotation but by magnetic reconnection events. In this context, quark stars could form a subset of magnetars, differentiated only by their internal composition. Rotational dynamics are further affected by the extreme compactness of quark stars. Their smaller radius allows for faster rotation without breakup, potentially enabling millisecond or even sub-millisecond pulsars. Some of the fastest known pulsars may already be quark stars masquerading as neutron stars, their true nature hidden beneath observational uncertainties. In the realm of gravitational wave astronomy, Quark Novae represent a promising but as yet undetected class of sources. The symmetry-breaking event of quark conversion could release a burst of gravitational radiation, albeit weaker than that from a merger. More likely, continuous gravitational waves from rapidly spinning, slightly deformed quark stars could be detected with long-term observations. These waves would carry the imprint of the star's internal structure and could reveal the rigidity and viscosity of quark matter. If quark novae are common, their cumulative effect over cosmic time would have significant implications for galactic evolution. They would enrich the interstellar medium with rare heavy elements and inject kinetic energy that could trigger star formation or alter the dynamics of gas clouds. In star-forming galaxies, regions with high neutron star density, such as the centers of globular clusters, might see occasional bursts of enrichment, perhaps contributing to the chemical anomalies seen in certain stellar populations. In binary systems, a quark nova could have devastating consequences. If the neutron star in a close binary with another massive star undergoes a quark nova, the resulting ejecta could strip the companion's atmosphere, disrupt accretion disks, or even unbind the system entirely. Alternatively, the system might survive, leading to unusual X-ray binaries or systems where a quark star continues to accrete matter, potentially triggering repeated emissions or even a delayed collapse into a black hole. In extremely tight binaries, such as double neutron star systems, the timing of a quark nova could be critical. If one neutron star converts to a quark star before merger, the dynamics of the eventual collision would differ substantially. The equation of state would be softer, the tidal disruption more extreme, and the gravitational wave signature altered. Detecting such a merger with LIGO, Virgo, or future observatories could reveal the fingerprints of a quark nova pre-merger, opening a new window into nuclear matter under stress. Another observational avenue lies in fast radio bursts, FRBs. These millisecond duration bursts of radio waves originate from cosmological distances and exhibit dispersion measures suggesting origin in dense plasma environments. While their origin remains debated, one hypothesis links them to quark novae. In particular, if the magnetic reconfiguration during the neutron-to-quark transition is rapid enough, it could release a sharp burst of electromagnetic energy in the radio band. If confirmed, this would place quark novae as progenitors of at least some FRBs, linking them to one of the most mysterious signals in modern astrophysics. If we broaden our perspective to the cosmological scale, quark novae may even play a role in the early universe. In the seconds after the Big Bang, temperatures and densities were sufficient for a quark-gluon plasma to exist across all of space. The transition from this primordial soup to hadronic matter may have left relics, phase boundaries, density fluctuations, or even quark nuggets that survive to the present day. These relics, if they exist, might form a component of dark matter or be responsible for certain unexplained cosmic ray events. Studying quark novae could therefore offer insight not just into stellar death, but into cosmic birth. In considering the broader cosmological implications of quark novae, one must delve into the idea that these events might act as natural laboratories for conditions mimicking those of the early universe. When a neutron star collapses into a quark star, it momentarily achieves energy densities and temperatures approaching those just microseconds after the Big Bang. This opens a window into the behavior of matter when the four fundamental forces were still undergoing decoupling and when quarks and gluons roamed freely. By analyzing Quark Nova models and their ejecta, researchers attempt to infer properties of the quark-gluon plasma that once permeated the cosmos. Unlike the early universe, however, a quark nova is not uniformly expanding. Its dense core provides constraints that allow for isolated conditions to persist, allowing us to model transitions with far more local precision than a universal simulation could provide. Furthermore, there is growing interest in whether quark novae might contribute to cosmic reionization or early heating of the intergalactic medium. During the epoch of reionization, ultraviolet light from the first stars is believed to have reionized neutral hydrogen. But if quark novae were present in sufficient numbers during this era, either as isolated events or in dense protogalactic regions, their combined emissions might have played a supporting or even dominant role in that transformation. Each event releases immense radiation, including high-energy gamma rays and neutrinos, all of which contribute to ionization and thermal feedback in surrounding gas clouds. In turn, this could affect the formation rate and mass distribution of second-generation stars. In terms of the physical manifestation of the quark nova, it is worth noting the internal layers it might possess post-transition. At the very core lies the densest region, potentially composed of color-flavor-locked CFL, quark matter. Here, all three types of quarks, up, down, and strange, pair up via the strong force to form a condensate that is incompressible and exhibits properties akin to a perfect fluid. Above that may lie a crust of less exotic but still deconfined quark matter, possibly a two-flavor superconducting, 2SC, phase dominated by up and down quark pairing. Further outward, the transition zone may gradually re-establish the structure of nucleons before giving way to a thin crust of normal matter, possibly composed of heavy nuclei suspended in a degenerate electron sea. These layered structures are purely theoretical at this stage, but their thermodynamic and mechanical properties influence everything from thermal conductivity to rotational inertia to magnetic field generation. An especially captivating concept involves the emission of strangelets, small, stable aggregates of strange quark matter, during the explosive phase. These hypothetical particles could travel across interstellar space and, if sufficiently stable, reach Earth. Strangelets are theorized to have a very low charge-to-mass ratio, making them difficult to detect via conventional cosmic ray observatories. Some physicists have speculated that strangelets could occasionally be responsible for unexplained ultra-high-energy cosmic ray events that exceed the Greason, Zatsepin, Kuzmin, GZK limit. Unlike protons, strangelets would not lose energy as easily over cosmic distances, enabling them to arrive at Earth with their full energetic load intact. There's even a speculative avenue where strangelets interact with normal matter in exotic ways. One concern, though largely dismissed, is that a stable strangelet could catalyze a transformation of ordinary matter into strange matter, a runaway reaction with catastrophic implications. While the probabilities are vanishingly small and the conditions required nearly impossible to achieve outside of carefully contrived thought experiments, it's a chilling reminder of how little we truly understand about the stability boundaries of matter under extreme conditions. In neutron stars poised for a quark nova, the presence of hyperons, particles containing strange quarks such as the lambda or sigma baryons, can act as a precursor. As the neutron star continues to accrete matter or spin down, the appearance of these hyperons may signal the approach of the critical density required for deconfinement. Their emergence softens the equation of state, increasing the likelihood of a gravitational collapse. When quark matter finally nucleates, perhaps in a single point or a small region, the process accelerates uncontrollably. A combustion front races outward at relativistic speeds, converting the surrounding neutron-rich matter into quark matter, releasing vast amounts of latent heat in the process. It's this phase transition that drives the explosion, and it may be further complicated by the emission of neutrinos. Just as in a core-collapse supernova, the sudden conversion of matter releases a flood of neutrinos, tens of trillions of them per square centimeter per second for brief periods. These neutrinos could carry away a significant fraction of the total energy, up to 10 to the power of 53 ergs in some models, though their detection remains a challenge. A nearby Quark Nova could flood detectors like Super Cameo Candy or Ice Cube with a distinctive burst pattern, potentially differing from that of a classic supernova by energy spectrum and time profile. This signal, if matched with electromagnetic observations, could offer a definitive identification of a quark nova. The role of Quark Novae in our process nucleosynthesis is particularly intriguing. In traditional models, rapid neutron capture is thought to occur in core-collapse supernovae or neutron star mergers, but these environments come with challenges, chief among them the difficulty in achieving the necessary neutron flux. Quark novae, especially those occurring shortly after a supernova, offer a unique setting, high neutron density, relativistic outflows, and a backdrop of freshly synthesized heavy nuclei. The additional shock may trigger further nuclear processing, especially of nuclei with mass numbers greater than 130. This could help explain some of the isotopic abundances observed in metal-poor stars, whose compositions are thought to reflect the nucleosynthetic environment of the early galaxy. Even more provocatively, some researchers have explored whether Quark Novae might be responsible for the so-called lithium problem, the discrepancy between predicted and observed amounts of lithium-7 in the universe. In certain models, the secondary shock of a quark nova could destroy or enhance lithium via spallation reactions, depending on timing and composition. While this remains speculative, it's one of many avenues through which quark novae might fill gaps in existing cosmological models. Turning our attention to detection prospects, there are numerous observational signatures that astronomers now search for, often hidden within broader data sets. These include double-peaked light curves, unusually high kinetic energies in supernova ejecta, extended plateaus in luminosity, or spectral evidence for exotic heavy elements not easily produced by known processes. Future observatories with greater sensitivity and time resolution may be able to pick out these features more clearly. Instruments such as the Vera-C, Rubin Observatory, the European Extremely Large Telescope, and the proposed Einstein telescope for gravitational waves all promise to shed light on these cosmic enigmas. Quark stars, the remnant compact objects left behind, would themselves exhibit unique behaviors. Their radii could be as small as 8 to 10 kilometers, compared to the usual 12 to 15 kilometers for neutron stars, yet contain similar or even greater masses. Their density profiles would differ dramatically, lacking a rigid crust or perhaps only possessing one a few hundred meters thick. Thermal emission from the surface would also be distinct, cooler in some models, hotter in others, depending on whether color superconductivity suppresses or enhances neutrino losses. If a quark star remains magnetized, its magnetic topology might evolve differently over time. Magnetic field decay, reconnection events, and crustal shifts would be governed by the unique conductivity and mechanical properties of quark matter. As such, we might expect novel forms of magnetar activity or even previously unclassified transient phenomena, brief, intense flashes of X-rays or gamma rays with recurrence intervals set not by external accretion but by internal magnetic instability. Another speculative but compelling avenue lies in the possibility of rotational instabilities. In particular, the R-mode instability, where the star's rotation couples with gravitational wave emission, could act more efficiently in quark stars, especially if their interior viscosity is suppressed by superfluidity or color superconductivity. This could result in rapid spin-down episodes, coupled with bursts of gravitational waves. If detected, such a signal would not only confirm the star's compactness but potentially reveal properties of dense quark matter directly. These rotational instabilities, particularly the R-mode instability, serve as a unique probe into the star's internal composition. In neutron stars, viscous damping typically suppresses these modes unless certain conditions, like low temperatures or specific rotation rates, are met. But in quark stars, especially those in a color-flavor locked state, the shear and bulk viscosities could be markedly different. Color superconductivity may allow these oscillations to persist longer, increasing the amplitude of gravitational wave emission and making them more observable with next-generation detectors. The emission patterns from such events would be quasi-monochromatic and long-lasting, and with enough sensitivity, could provide the clearest fingerprint yet of a quark star. Delving deeper into the gravitational wave implications, if a quark nova does indeed occur as a secondary explosion following a supernova, the dynamics of that interaction could lead to detectable ripples in spacetime. Imagine a neutron star collapsing into a quark star and ejecting matter outward in an asymmetric fashion. This asymmetric ejection, combined with rapid rotation, might generate a brief but powerful burst of gravitational waves. Unlike those from neutron-star mergers, these would be singular events, lacking the complex chirp signal, but might carry a unique frequency spectrum tied directly to the conversion front moving through the neutron star core. These are the kinds of theoretical fingerprints that data analysts are beginning to comb through, especially in unexplained gravitational events that don't fit known categories. Even the physics of the conversion front itself is rich with complexity. It behaves like a combustion front, not unlike a deflagration or detonation wave in chemical explosives. But in this case, it's converting baryonic matter into a soup of deconfined quarks. The exact mechanism is debated. Some suggest a deflagration front propagates subsonically with the help of neutrino diffusion, while others propose a detonation that races through the star at supersonic speeds. There's even the possibility of a hybrid scenario, where a slow-burning front is followed by a transition into a faster detonation due to pressure feedback or turbulence. Each scenario predicts different energies, timescales, and ejected mass, and thus could be identified observationally with precise light curves and neutrino signals. A fascinating side effect of this conversion is the production of antimatter. In certain high-energy conditions at the conversion front, there's a non-negligible chance for quark-antiquark pairs to be formed, and while most will annihilate quickly, a tiny fraction might escape the dense environment. These positrons and antiprotons could mix with the surrounding interstellar medium, leading to faint but persistent annihilation signals. This is another observational frontier, especially with upcoming space missions capable of detecting low background gamma rays. Should an unexplained 511 keV line or a diffuse annihilation halo be traced to a recent supernova remnant, it might hint at a quark nova in the past. The compactness of the remnant quark star also alters its interaction with nearby environments. A highly compact object with a stronger gravitational gradient can accrete material more efficiently, potentially igniting episodes of X-ray bursts unlike those seen in neutron stars. These so-called strange star bursts might appear superficially similar to Type 1 X-ray bursts but show anomalies in recurrence time, peak luminosity, or spectral hardness. In accreting binary systems, these differences could become apparent over extended observation campaigns. Some candidate systems, like the enigmatic source XDEJ 1739-285, have already shown unusual bursting behavior that could point to a strange or quark star as the accretor. In modeling these systems, one must also account for thermal evolution. Neutron stars cool primarily via neutrino emission from their interiors and photon emission from their surfaces. Quark stars, depending on the phase of quark matter, may exhibit radically different cooling curves. For instance, in the color-flavor-locked phase, pairing gaps suppress most neutrino interactions, leading to slower cooling and a hotter surface over time. This might explain some isolated compact objects that appear too hot for their age, such as RxJ 1856.5, 3754, which traditional neutron star models struggle to account for. Conversely, if neutrino emission is enhanced via new mechanisms, a quark star might cool faster, becoming faint and hard to detect only a few thousand years after formation. These divergent pathways highlight the importance of long-term thermal monitoring across multiple wavelength bands. But perhaps the most daring idea in Quark Nova theory is the possibility that some of these compact objects don't just stop at becoming quark stars. They collapse further, forming black holes. This could occur in two ways. First, the core mass might exceed the Tolman, Oppenheimer, Volkoff limit even after converting to quark matter, in which case the object has no stable endpoint and continues collapsing. Second, the loss of pressure support during the conversion might cause a sudden implosion, leading to prompt black hole formation. In either case, the result is a very fast, very energetic event with minimal remnant. These failed Quark Novae could appear as extremely brief gamma ray bursts, perhaps even some of the mysterious, dark, bursts that lack optical counterparts. There's also speculation that a quark nova in a binary system could serve as a trigger for exotic astrophysical phenomena. If a white dwarf is in close orbit with a neutron star that undergoes a quark nova, the shockwave and ejecta could compress the white dwarf to the point of ignition, leading to a Type I supernova-like event. This sequence, quark nova-triggered thermonuclear explosion, has been proposed as a mechanism for some superluminous supernovae that otherwise defy categorization. Unlike classical Type I events, which involve the white dwarf alone, this would involve both stars and might result in asymmetries, unusual light curve durations, and mixed element ejecta. On a cosmic scale, the cumulative effect of quark novae could even influence galactic evolution. Consider the injection of kinetic energy, heavy elements, and relativistic particles into the interstellar medium. Each quark nova deposits an enormous amount of momentum and matter, potentially seeding future star-forming regions or blowing cavities into galactic disks. In dwarf galaxies or early starbursts, a few well-timed quark novae might suppress or enhance star formation significantly. This feedback mechanism is often overlooked but might help explain irregular star formation histories in metal-poor systems observed by the Hubble Space Telescope and the James Webb Space Telescope. A final frontier in the study of quark novae lies in experimental physics, particularly in the search for stable strange matter. If strange quark matter is truly the ground state of baryonic matter, as the Bodmer-Witten hypothesis proposes, then even a single detection of a strangelet on Earth would revolutionize our understanding of physics. High-altitude balloon experiments, deep space probes, and even particle colliders have been considered as possible sites of discovery. The Large Hadron Collider and the Relativistic Heavy Ion Collider have both created quark-gluon plasmas, though only for infinitesimal times and volumes. A naturally occurring quark nova would dwarf these experiments, producing strange matter in quantities and durations unmatched on Earth. The capture and study of even one such fragment could confirm decades of theory and spark new fields of applied physics and materials science. In contemplating the broader ramifications of strange quark matter escaping from a quark nova, one must seriously consider the possibility that some of these ejected fragments could remain stable and persist in space for cosmological timescales. These fragments, or strangelets, might range in size from microscopic nuclei-like clumps to asteroid-scale bodies, depending on the details of the ejection and the conditions during cooling. If strangelets are stable and possess a lower energy per baryon than normal matter, then any interaction between them and regular atomic nuclei could potentially catalyze a conversion process, transforming ordinary matter into strange matter upon contact. This possibility, though speculative, is one reason why the idea of strangelets has been approached with both fascination and caution. The universe may serve as a natural laboratory for this process, especially in environments with high density and turbulence. The galactic core, for instance, is a region saturated with gravitational interactions and star death. If strangelets are emitted during a quark nova, and if they are stable, then over billions of years some may have migrated inward, captured by galactic gravity wells. There, they might reside undetected, embedded within stars, planets, or even drifting alone in the interstellar medium. If they interact rarely or weakly with normal matter, they may escape notice. But a single interaction, a strangelet passing through Earth or striking a spacecraft, could leave behind clues in the form of anomalous energy traces, unexplained material transformations, or exotic particle emissions. Detecting these strangelets remains an active challenge in modern astrophysics and particle physics. Some proposed detection methods involve monitoring for unusual cosmic rays, particularly those with extremely high mass-to-charge ratios that cannot be explained by known atomic nuclei. Others suggest using ultra-sensitive cryogenic detectors buried deep underground or mounted on satellites, designed to pick up the rare but distinctive energy signatures of strangelet collisions. Despite decades of effort, no confirmed detections have occurred, yet the absence of evidence is not evidence of absence. The parameter space for these objects is vast, and many believe it is only a matter of time before advances in detection capability intersect with the rare path of a strangelet. In addition to the physical consequences, the idea of strangelets and Quark Novae raises deep philosophical questions about the nature of matter and the ultimate fate of the universe. If strange matter is indeed more stable than regular matter, could there be entire galaxies or regions of space composed primarily of strange stars and strange planets? Could the visible universe be only one phase among many, with hidden pockets where quark matter dominates? Some cosmological models even speculate that the early universe, in the moments following the quark-hadron transition, may have momentarily favored strange matter, only for it to later become unstable as temperatures dropped. If that fleeting phase was preserved in a few locations, perhaps shielded from expansion or reheated by collapsing gravity wells, those regions could still exist today, like fossils from an alternative past. Furthermore, the theoretical implications extend into quantum gravity and string theory. In these frameworks, the behavior of matter under extreme conditions, such as those inside a quark nova, becomes a testbed for ideas that cannot yet be verified on Earth. The behavior of the strong force, the coupling between color charges, and the breaking and restoration of chiral and conformal symmetries all become relevant at the densities achieved during a quark nova explosion. Some string-theoretic models even propose that under such pressures, additional dimensions or brane interactions may briefly become accessible, leading to exotic decay channels or the appearance of higher-dimensional particles. These speculations remain beyond our current ability to test, but the energies and densities produced in a quark nova may represent our best chance of observing such phenomena naturally. The connection between quark novae and dark matter is another frontier that remains largely unexplored but highly provocative. Dark matter, which constitutes the vast majority of the mass in the universe, has eluded direct detection for decades. One speculative idea is that at least part of the dark matter population could be composed of compact, electrically neutral strangelets, dense clumps of quark matter that interact weakly with photons and baryons. Such particles would be difficult to detect directly, but they would exert gravitational influence, just as observed in galactic rotation curves and gravitational lensing studies. If this hypothesis is true, then quark novae might not only be rare astrophysical phenomena, they might be the primary generators of one of the most mysterious components of the cosmos. Meanwhile, the thermodynamics of a quark nova is itself a compelling study. As the neutron star's core collapses into quark matter, a massive amount of latent heat is released. This energy is not simply radiated away, it drives the explosive ejection of the crust, energizes neutrino production, and shapes the dynamics of the blast wave. In high-resolution numerical simulations, the temperature inside the core can briefly reach hundreds of MeV, approaching levels seen in the early universe microseconds after the Big Bang. At these energies, the line between individual particles and collective fields begins to blur. Quarks and gluons may behave more like a strongly coupled fluid than individual particles, leading to surprising phenomena such as viscosity suppression and perfect fluid behavior, a state sometimes called the quark-gluon liquid. Observationally, there may be a critical energy signature from the interaction between this ultra-hot fluid and the cooler outer layers of the star. This interaction could drive strange phase transitions or turbulent mixing, leading to a rapid change in opacity, and therefore, a brief, sharp pulse in the emitted light curve. Such a pulse might appear as a precursor flash or as a high-energy tail in the supernova spectrum, features that can be distinguished with sensitive spectroscopy, especially in the UV and gamma-ray bands. Some candidates, like SN 2006 GY and SN 2015 billion, have shown unusual early emission profiles that defy conventional supernova models and might be indicative of quark nova precursors. In terms of nuclear chemistry, the matter ejected during a quark nova may exhibit highly unusual isotopic ratios. Standard nucleosynthesis in supernovae leads to a distribution dominated by iron peak and alpha elements. But in the neutron-rich, high-energy environment of a quark nova ejecta shell, rapid neutron capture, the R process, could proceed even more efficiently, creating super-heavy elements with atomic numbers far beyond those seen in nature. These elements would be unstable, of course, but their decay products might leave telltale fingerprints in old stellar populations or in the interstellar dust of the Milky Way. Theoretical predictions suggest the possible formation of elements in the so-called island of stability, a region of the nuclear chart where superheavy nuclei may exhibit relatively long half-lives due to shell effects. If these elements exist and can be traced back to specific supernova remnants, it would be powerful indirect evidence for the existence of Quark Novae. And this brings us to a perhaps poetic, yet scientifically grounded idea, that Quark Novae, in their role as cosmic alchemists, may be partly responsible for the most mysterious elements in the periodic table. The heavy actinides and transuranic elements, used today in nuclear reactors and experimental physics, may owe their existence not solely to neutron star mergers or rare supernovae, but to the even rarer, more explosive, and more transformative Quark Novae that scattered strange nuclei across the stars. It's a humbling realization that some of the atoms in our own bodies may have originated in a cataclysmic flash of quark glue on fire, reshaping not only matter, but the very possibilities of chemistry and physics. These strange possibilities are not confined to mere abstraction. They lead directly into the pressing question of cosmic evolution and the distribution of matter and energy in the observable universe. The sheer violence of a quark nova and the extreme energies involved may act as cosmic accelerators, seeding the universe with not just particles and nuclei, but also with energy and turbulence that can affect galaxy formation. In the vast webs of matter that stretch between galaxies, the early presence of quark novae might have introduced powerful shockwaves, ionizing vast volumes of gas and altering the conditions under which protogalaxies coalesced. While this remains speculative, some cosmological simulations show that even a small number of highly energetic point sources, like quark novae, early in the universe's history could create lasting anisotropies in baryonic matter distribution. Additionally, the imprint of a quark nova may persist in the cosmic microwave background (CMB), not as direct radiation from the event itself, since that would be redshifted into oblivion over billions of years, but through its influence on nearby matter and its heating effect on surrounding clouds. If quark novae occurred in dense star clusters or early galaxy halos, the reionization of hydrogen gas they may have triggered could create subtle patterns in the CMB. These secondary anisotropies, such as the Sunyaev-Zeldovich effect, could provide indirect evidence of early, ultraviolet stellar deaths beyond the capacity of ordinary supernovae. The electromagnetic signatures of a quark nova are themselves fertile ground for exploration. Quark novae are expected to produce intense gamma-ray bursts, GRBs, X-ray flares, and optical transients, but the timing and spectrum of these emissions may differ from traditional GRBs or Type II supernovae. In particular, a delayed GRB, occurring hours or days after a supernova-like event, could hint at a two-stage collapse. First, the formation of a neutron star and a classic quark-collapse supernova, followed by a secondary collapse of the neutron star into a quark star, producing a quark nova. This two-stage model would leave behind a complex, layered light curve with multiple peaks and varying timescales, something that has already been hinted at in several anomalous GRB events recorded by observatories like Swift and Fermi. Moreover, gravitational waves represent an entirely different observational window into the quark nova phenomenon. When a neutron star collapses into a quark star, the asymmetry in its structure and the sudden redistribution of mass may emit a powerful burst of gravitational radiation. This wave could carry a distinct signature, differing from the chirps produced by black hole mergers or the longer signals from neutron star mergers. Detectors like LIGO, Virgo, and the upcoming Einstein telescope may one day be able to capture these signatures, providing direct evidence of quark deconfinement under astrophysical conditions. In fact, the discovery of gravitational waves from unusual or unexplainable events in the near future could spark a re-evaluation of previously catalogued events and prompt a search for the fingerprints of quark matter transformation. Yet perhaps the most captivating idea lies in the possibility that quark stars themselves, born from these explosive transitions, persist as unique celestial objects. Unlike neutron stars, quark stars could have very different surface properties. Their crusts, if they exist at all, might be only a few hundred meters thick. Beneath lies a sea of deconfined quark matter, strange, up and down quarks bound in a fluid, with densities millions of times greater than atomic nuclei. The magnetic fields of such stars could be even more extreme than those of magnetars, and their rotational behavior could deviate from known pulsar models. Quark stars might exhibit sudden frequency glitches or rare electromagnetic emissions unlike any currently known neutron star behavior. Identifying such an object would be a monumental achievement. Astronomers have already catalogued a few neutron stars that defy classification, objects like RxJ 1856.5, 3754 and 1E 1207.4 to 5209, whose thermal emissions or spin properties do not align well with standard models. While none have yet been confirmed as quark stars, their anomalies have triggered renewed interest in reanalyzing old data with quark matter models in mind. Additionally, isolated compact stars with unexpectedly low radii or unexplained cooling behavior may soon offer the first firm candidates for quark stars, especially as new X-ray telescopes like NICER and Athena push the boundaries of compact star observation. There is also the cultural and intellectual curiosity surrounding Quark Novae. These events are not just physical explosions, they are gateways to understanding the most fundamental aspects of matter. They test our comprehension of the strong nuclear force, confinement, and the behavior of color charge in QCD. If even one quark nova were conclusively identified, it would validate decades of theoretical physics and open the door to entire new branches of astrophysics. It would signal that the universe is far stranger and more diverse in its matter states than we ever imagined, and that our cosmic history includes phases, transformations, and phenomena yet to be fully appreciated. In theoretical simulations, the moment of quark nova detonation is modeled as a violent collapse where the core contracts in milliseconds, releasing immense energy. The transition occurs not gradually but as a sharp phase boundary sweeps outward from the center. This boundary separates hadronic matter from quark matter, and its passage is marked by shock heating, neutrino bursts, and rapid particle acceleration. These dynamics make the modeling of quark novae extraordinarily complex, requiring general relativistic hydrodynamics, nuclear reaction networks, and neutrino transport equations. Even state-of-the-art supercomputers struggle with these simulations, and most require simplifications or approximations. Nonetheless, the emerging results are painting a clearer picture, and each run brings us closer to a full understanding of the mechanisms behind these cosmic juggernauts. Neutrinos, in particular, play a vital role in this story. When the quark nova occurs, an enormous burst of neutrinos is released, perhaps rivaling or even surpassing the output of a typical supernova. These particles, nearly massless and barely interactive, escape from the core and stream across the cosmos. If a future neutrino observatory such as Hypercameo-Candy or IceCube Gen 2 detects a sudden, intense burst of neutrinos unaccompanied by a traditional optical supernova signature, it might be the first direct evidence of a quark nova. Even more intriguingly, if this burst is followed by a delayed electromagnetic flash or unusual gamma-ray event, the case for a two-stage stellar death becomes compelling. We are also forced to consider the fate of binary systems where quark novae might occur. In tight binaries, a quark nova could dramatically alter the dynamics of the system. The explosive ejection of mass could either tighten or destabilize the orbit. If the quark nova occurs in a system where the companion is a white dwarf or another neutron star, the resulting shockwave could strip material or even trigger a secondary collapse or thermonuclear reaction. These interactions might give rise to entirely new classes of supernova-like events, what some researchers have referred to as QNI explosions, a quark nova-induced detonation of a white dwarf. These hybrid events could help explain some of the diversity in type Ia supernova light curves and may offer a new standard candle for cosmological measurements. Even more exotic is the idea that the remnants of a quark nova, either a quark star or a strangelet cloud, could interact with its surroundings in complex and long-lasting ways. Over time, this interaction could lead to gradual conversion of surrounding matter into strange matter, if stability conditions allow. This creeping conversion might slowly change the mass, composition, and radiation signature of nearby objects. If this process is real, it suggests a potentially self-replicating mechanism for spreading strange matter, albeit one that would proceed incredibly slowly on astronomical timescales. Still, it raises profound questions about whether our galaxy has always been dominated by normal matter, or whether quiet, ongoing transformations have been altering that balance in ways we cannot yet detect. The possibility of controlled quark matter on Earth also looms large. If future particle colliders reach the energies required to produce stable quark matter or strangelets, we will face unprecedented ethical and scientific questions. Could a strangelet be safely contained? Could it catalyze a chain reaction? These concerns were raised during the development of the RHIC and the LHC, although no strangelets have yet been observed in experiments. Still, the prospect remains, not just as a threat, but as a tantalizing promise of harnessing one of the most powerful forms of matter in the universe. In the shadow of these immense possibilities lies the profound realization that Quark Novae are not merely astronomical events but revelations of nature's deepest architecture. They represent a phase transition in the very building blocks of reality. The moment a neutron star succumbs to the pressure and crosses into the quark matter state, it's as if nature herself is unlocking a forbidden chamber, where protons and neutrons dissolve, boundaries blur, and a new order of matter asserts itself. This transformation is not subtle. It is explosive, world-altering, and, perhaps most importantly, inescapable when the conditions align. When examining this further, one must consider the various phases of quark matter. Quark matter does not exist in a singular form. There is believed to be a rich phase diagram that includes strange quark matter, color superconducting phases, and other more exotic configurations. Each phase could have different thermodynamic properties, cooling rates, viscosities, and emission profiles. The concept of color superconductivity, where quarks pair up in a manner similar to electrons in a superconductor, is especially fascinating. These phases could dramatically change the stability and emission characteristics of the resulting quark star. Some phases may be transient, rapidly decaying into others, while some might be stable for billions of years. Others may only occur in the moments immediately following the detonation, yet leave indelible imprints on the composition of the ejecta or the gravitational signature of the event. As we journey through this theoretical territory, we encounter the concept of strange quark matter being the true ground state of matter. This hypothesis, often called the strange matter hypothesis, posits that under certain conditions, the combination of up, down, and strange quarks is more stable than normal nuclear matter. If this is correct, then all ordinary matter is, in a sense, metastable, and given the right trigger, such as a strangelet or a quark nova, could transition into this lower energy state. The implications are staggering. A sufficiently stable strangelet could, in theory, initiate a chain conversion process, transforming nearby normal matter into strange matter. Although there is no empirical evidence yet of such a process occurring naturally, the theoretical framework is robust enough to warrant continued caution and continued fascination. There are also interesting links between Quark Novae and the broader study of compact object evolution. For instance, some millisecond pulsars, rapidly spinning neutron stars, might actually be quark stars. Their unusual stability, small radii, and surprisingly low magnetic fields in some cases defy the expectations of neutron star models. If these pulsars were once neutron stars that underwent a quark nova, their observed properties might be a natural result of that transformation. Additionally, the intense spin down of these stars over time, due to magnetic braking or gravitational wave emission, might serve as indirect evidence of their internal composition. Precise timing studies and X-ray pulse profiling could eventually reveal the hidden quark nature of these enigmatic objects. Another avenue of exploration lies in nucleosynthesis. As mentioned earlier, Quark Novae might be the missing puzzle piece in the story of the heaviest elements. The R process, or rapid neutron capture process, requires environments rich in free neutrons and capable of sustaining extreme energy levels long enough to build up atomic nuclei to uranium and beyond. Traditional core collapse supernovae struggle to provide the required conditions in sufficient quantity to explain observed elemental abundances, especially in the early universe. Neutron star mergers provide a better environment, but the frequency and timing of such events may not account for heavy elements found in extremely old stars. Quark Novae, especially those occurring shortly after the formation of the first stars, may solve this problem. Their ejecta, rich in neutrons and unbound nucleons, and expanding at relativistic velocities, could be the ideal site for forging rare elements. This could help explain the peculiar isotopic patterns found in ancient stellar populations, meteorites, and even Earth's crust. The expanding shock front of a quark nova is also an area of intense study. This front, moving at relativistic speeds, plows through the surrounding medium with immense force. As it does so, it creates conditions ripe for particle acceleration. Electrons caught in the magnetic fields of the shock may spiral at nearly light speed, emitting synchrotron radiation. Protons may be accelerated to ultra-high energies, potentially contributing to the population of cosmic rays that bombard Earth from space. The connection between quark novae and high-energy astrophysics thus becomes even more intimate. These events may be part of the solution to the origin of ultra-high-energy cosmic rays, a long-standing mystery in astrophysics. Looking further into the observable universe, there is speculation that some superluminous supernovae, those that are 10 to 100 times brighter than a typical supernova, could in fact be the visible expression of quark novae. These events are too bright, too long-lasting, and too energetic to be explained by standard models. The injection of additional energy from a delayed quark nova, following an initial core collapse, could provide the boost needed to account for the observed luminosity. If true, then a fraction of these seemingly anomalous supernovae may not be supernovae at all, but the glowing remnants of quark matter being born in the hearts of dying stars. We must also address the philosophical implications of quark novae. They challenge the simplicity of death in the universe. A star's life no longer ends in a single, final act. Instead, it may end in a cascade, a sequence of deaths, each revealing a deeper layer of reality. First, the hydrogen runs out. Then comes the collapse, the birth of the neutron star. But the collapse may not be finished. The neutron star, under further strain, gives way again, to something stranger. Each stage is a deeper fall into the structure of matter, and in each fall, nature reveals more of herself. The existence of quark novae is a stark reminder that even our most extreme observations may still be scratching the surface. In the context of galaxy formation and evolution, the feedback effects of quark novae may be far greater than previously imagined. These explosions may regulate star formation in dwarf galaxies or the outskirts of larger galaxies, suppressing or enhancing the formation of new stars depending on the energy and timing. A single quark nova in a dense star-forming region could inject so much energy that the gas is blown out, halting star formation for millions of years. Alternatively, the shockwaves could compress gas clouds, triggering new waves of collapse. Either effect, on a galactic scale, would be profound. As we study high-redshift galaxies and the earliest stars in the universe, so-called population 3 stars, quark novae may once again come to the forefront. These first-generation stars were massive, metal-free, and short-lived. Many likely ended their lives as massive black holes, but others may have become neutron stars. If so, the mass and energy conditions for quark novae might have been met frequently. This would make quark novae some of the first and most powerful explosions in the universe's history, perhaps rivaling even the energy scales of the Big Bang in their localized effects. In terms of detectability, we are approaching the dawn of a new era. With next-generation observatories, both terrestrial and space-based, coming online, we will soon have the tools to search systematically for the fingerprints of quark novae. The Vera C. Rubin Observatory will scan the entire sky for transient events, capturing light curves with unprecedented detail. The James Webb Space Telescope may detect ancient infrared flashes consistent with early quark novae. Meanwhile, gravitational wave detectors will improve sensitivity, and new neutrino observatories will cast their gaze deeper into the cosmos. A single confirmed detection from any of these instruments could rewrite the textbooks, not only on stellar evolution, but on the very nature of matter. And yet, the most exciting thing about quark novae may be that we have only just begun to imagine what they could mean. They could serve as a bridge between the microscopic and the macroscopic, between the quantum realm of quarks and gluons and the cosmic scale of galaxies and star clusters. They are where the smallest and the largest meet, where the rules of particle physics and astrophysics converge. In them, we see the power of nature not just to create but to transform, to reveal hidden structures, to shift states of being, to transition not only stars but theories themselves into new forms. The birth of a quark star through a quark nova may also redefine our understanding of what it means for an object to be compact. Traditionally, we have viewed neutron stars as the ultimate endpoint of compression, densities higher than an atomic nucleus, matter packed into a city-sized sphere with the mass of our Sun. But quark stars could take this further. If strange quark matter is more tightly bound, then quark stars may have smaller radii than neutron stars of equivalent mass. This would imply a staggering increase in density, one that may approach or exceed the theoretical limits of our understanding of degenerate matter. This opens a doorway to exploring how general relativity handles such exotic configurations, and whether modifications to our gravitational models are needed at these scales. One of the striking implications of this density difference is its potential detectability via precise mass-radius measurements. If a compact object has a mass consistent with a neutron star but a radius significantly smaller than expected, this anomaly could be an indirect clue pointing toward quark matter. Upcoming X-ray missions like NASA's NICER, Neutron Star Interior Composition Explorer, are designed to carry out exactly these kinds of measurements. By studying the thermal emission and surface pulsations of compact stars, astronomers can infer the object's shape and size, and potentially identify candidates for quark stars hiding among the known pulsar population. Furthermore, the thermal evolution of quark stars may differ sharply from neutron stars. In the initial moments after a quark nova, the temperature of the newborn quark star could exceed 1 trillion Kelvin. As it cools, it emits neutrinos at a prodigious rate, cooling faster than its neutron star predecessor. However, depending on its composition, such as whether it's in a color-flavor-locked CFL phase or a 2SC, two-flavor superconducting phase, this cooling may stall, or even result in unexpected thermal signatures. Observing anomalously cold or hot compact stars could therefore provide indirect evidence of quark matter. Another fascinating area of speculation involves the interaction of quark nova ejecta with the surrounding environment. The initial supernova often leaves behind a complex structure of dust, gas, and heavy elements, forming a nebula. When a quark nova occurs, the second explosion slams into this previously ejected material. The result is a re-energization of the nebula, possibly leading to extremely bright emission over a broad spectrum. Such dual explosion signatures would be unique. Optical telescopes could see an unusually long and energetic light curve. Radio telescopes might detect synchrotron radiation from accelerated electrons in the magnetic fields. X-ray and gamma-ray observatories could witness flashes of high-energy particles. This multi-wavelength observability gives astronomers a promising toolkit to identify candidate quark novae in the data. There's also an emerging hypothesis that the strange matter produced in quark novae could escape into space as strangelets, tiny droplets of stable strange quark matter. These strangelets, if they possess the right stability and electric charge, could travel vast distances through the galaxy without decaying. Some might even reach Earth. Experiments such as AMS-02, Alpha Magnetic Spectrometer, aboard the International Space Station are searching for anomalous particles that could be strangelets. Detecting one would be an incredible breakthrough, proving not only the existence of strange quark matter, but also confirming that quark novae occur and seed the galaxy with exotic material. Additionally, if strangelets are real and abundant enough, they might pose a risk to neutron stars. A single strangelet impacting a neutron star could, theoretically, catalyze a phase transition in that star, transforming it into a quark star in a runaway reaction. This leads to the unsettling notion that quark novae could be contagious on a cosmic scale, where one event triggers a cascade of conversions across neighboring systems. While this remains speculative, it provides a thrilling theoretical angle that makes the study of quark novae even more urgent and relevant. The implications extend beyond pure physics into the realm of cosmic history. Quark novae, if they occurred with sufficient frequency in the early universe, could have seeded galaxies with heavy elements much earlier than previously thought. The iron, gold, and uranium in ancient star systems may owe their existence not to neutron star mergers or supernovae alone, but to quark novae acting as early, efficient factories of our process elements. This could help explain how some of the earliest known galaxies have unexpectedly high metal content, despite forming only a few 100 million years after the Big Bang. And what of black holes? A central question is whether a neutron star approaching the Tolman, Oppenheimer, Volkoff, TOV, limit, the point beyond which gravity overwhelms degeneracy pressure, always collapses into a black hole, or whether a quark nova might intervene first. If the quark transition provides enough pressure or energy to counteract collapse momentarily, it could prevent black hole formation, or at least delay it. This would introduce a new class of objects, metastable stars temporarily stabilized by quark matter. Such objects could exist for millions of years before finally succumbing, creating unique gravitational and electromagnetic signatures distinguishable from standard black hole or neutron star behavior. In terms of observational astrophysics, one of the most compelling goals is to identify a quark nova by its unique temporal light curve. A dual-peak supernova, where a bright initial explosion is followed days or weeks later by a second, brighter flash, would be a prime candidate. This time gap represents the delay between the initial core collapse supernova and the subsequent quark nova. Analyzing the energy, duration, and spectral shift of these two peaks could allow astronomers to distinguish quark novae from other multi-peak transients like parainstability supernovae or tidal disruption events. Moving into the realm of extreme theoretical possibilities, there are even suggestions that quark novae might be linked to gamma-ray bursts, GRBs. Some long-duration GRBs may involve a two-step mechanism. A massive star collapses into a neutron star, which then immediately or shortly after undergoes a quark nova, unleashing a relativistic jet of quark matter and radiation. If aligned with Earth, this jet could be detected as a GRB. The quark nova model could account for certain GRBs with unusual energy levels or afterglow characteristics that don't fit standard models. Even gravitational wave astronomy might one day confirm quark novae. The sudden collapse of a neutron star core into a quark star would produce a burst of gravitational waves distinct from those seen in binary mergers. These bursts would be of lower amplitude but higher frequency, potentially within reach of next-generation detectors like the Einstein telescope or Cosmic Explorer. Simultaneous detection of a gravitational wave and an electromagnetic counterpart, especially with a double light peak, could clinch the case for a quark nova. As we extend our theoretical modeling, simulations become indispensable. Modern supercomputers are now being used to simulate the complex dynamics of quark nova explosions. These simulations involve quantum chromodynamics, QCD, general relativity, magnetohydrodynamics, neutrino transport, and nuclear physics, all interacting in a chaotic environment of mind-bending extremes. Through these models, we begin to predict how matter moves, how heat diffuses, how shockwaves propagate, and how the boundary between neutron and quark matter evolves. These are not just mathematical curiosities. They are blueprints that guide observational efforts, suggest new instruments, and refine our understanding of the cosmos. Philosophically, the idea that matter is never truly at rest, never fully stable, even in its densest, most bound forms, speaks to a fundamental principle of nature. Transformation is eternal. The existence of quark novae is a testament to the dynamic, ever-changing universe we inhabit. Stars that die give birth to new kinds of matter. Explosions reveal hidden truths. The universe does not merely age, it evolves, deepens, and folds in on itself, revealing new layers of beauty and complexity. And perhaps most haunting of all, the reality of quark novae reminds us of how little we still know. These titanic events may have been happening across the galaxy for billions of years, yet we have never conclusively seen one. They may have created the gold in our wedding rings, the uranium in our reactors, the iron in our blood, and yet they remain in the shadows, hidden by distance, rarity, and our own limited imagination. But that is changing. We stand on the brink of a new age of discovery, armed with better tools, sharper theories, and a growing recognition that the universe is stranger than we ever imagined. Quark Novae are no longer theoretical whispers. They are knocking at the doors of our observatories, waiting to be heard, seen, and understood. And when we finally capture one, when the light curve flares, the neutrinos burst, the gravitational waves ripple through space-time, we will have glimpsed a truth deeper than stars, more primal than atoms, more eternal than time itself. This journey into the heart of Quark Novae begins to intertwine not only with the physical sciences but also with the broader philosophical and even existential implications of cosmic evolution. The very idea that a quark nova may occur after the death of a star invites us to reconsider what death means in a cosmic context. Just as life on Earth is punctuated by cycles of birth, transformation, and rebirth, so too are the stars. But in the case of Quark Novae, this rebirth is not merely about luminosity or pressure balance. It is a fundamental reconfiguration of matter itself, a journey to the deepest level of particle reality. In these moments, matter ceases to behave in familiar ways. Nuclei, once stable and compact, dissolve into their constituent quarks. Neutrons, which for so long represented the final state of collapsed matter, become temporary holding patterns in a much greater cosmic metamorphosis. Quarks, those most elemental building blocks of the universe, no longer confined to hadrons, are liberated, at least briefly, into a new state of existence, possibly one that is absolutely stable. This raises fundamental questions about the architecture of the universe. If strange quark matter is more stable than ordinary nuclear matter, then what we see, planets, stars, ourselves, is only metastable. Our entire reality may be balanced on a precipice of phase transition, held aloft by a less stable configuration of particles. And if that's true, the universe as we know it is not necessarily the most probable form the cosmos could take. This calls into question why it is the way it is. Why didn't everything decay into strange quark matter immediately after the Big Bang? Why does normal matter persist at all? Some theorists have speculated that the conditions of the early universe, high temperature, rapid expansion, and particle-antiparticle annihilation, may have provided a fleeting window where strange matter was not favored. But as the universe cooled, it locked in the less stable form. In this scenario, Quark Novae might represent not an anomaly, but a return to a more fundamental state of matter. Each event would then be a small echo of a deeper truth, revealing the underlying ground state of the cosmos. Let's now explore how the dynamics of a quark nova differ from those of a traditional core-collapsed supernova. In a typical supernova, a massive star ends its life when nuclear fusion can no longer counteract gravitational collapse. Iron builds up in the core, an element that cannot release energy through fusion, and the core collapses, creating a shock wave that blasts the outer layers into space. This event can release more energy in a few seconds than our Sun will emit in its entire 10 billion year life. But the quark nova takes this energy paradigm to a different level. After the neutron star is born, a second collapse can occur if the core pressure reaches a critical point where quark deconfinement is triggered. This isn't merely a collapse, it's a transformation. The density rises sharply, and the temperature surges to trillions of degrees. Matter is compressed into a state where up, down, and strange quarks exist in a free or semi-bound state. A shock wave emanates from the sudden change in the equation of state. A new pressure-density relationship takes hold, leading to a powerful release of latent energy. This second shock wave may catch up to the first supernova ejecta. When it does, the interaction can result in rebrightening of the explosion, an unusual supernova remnant with multiple energy injection points, and a complicated radiative history. This is why quark novae are such attractive candidates for explaining certain superluminous supernovae, SLSNA. These events are too bright and too long-lasting to be explained by traditional mechanisms. A dual shock process, where a quark nova re-energizes an earlier supernova shell, provides a compelling and mathematically consistent explanation. These dynamics also produce a rich environment for the rapid neutron capture process, or R process, to occur. The R process is responsible for creating roughly half of the elements heavier than iron, including gold, platinum, and uranium. Traditional models struggle to produce sufficient R process elements in regular supernovae, and while neutron star mergers have emerged as strong candidates, they may not be frequent enough to account for the observed abundance. Quark Novae, with their dense ejecta, neutron-rich environment, and powerful shockwaves, offer a viable alternative site. If they occurred more often in the early universe than they do now, they could have played a crucial role in seeding the cosmos with the heavy elements necessary for planets and life. Now imagine this. A quark nova occurs in a binary star system. The companion star, still alive and burning, is suddenly bombarded with radiation, particles, and shock waves from the quark nova. The impact could strip away its atmosphere, destabilize its orbit, or even trigger new fusion reactions in its outer layers. Alternatively, if the system is tight enough, the companion could accrete material from the quark nova, becoming enriched with heavy elements. Such systems may look very different from ordinary binaries. Their spectra might show unusual element abundances, or they may emit high-energy bursts that don't align with known stellar activity. Searching for these anomalies in our galaxy's binary star population could be a way to identify past quark nova events. Even more exotically, what if a quark nova occurred near a planetary system? The energy output, although smaller than a gamma-ray burst, would still be colossal. Any nearby planets would be sterilized or vaporized. If intelligent life had evolved there, it would be wiped out in an instant. This brings us to the speculative but intriguing concept of cosmic natural selection. Could the frequency of catastrophic events like Quark Novae help shape the evolution of life in the universe? Are we living in a quiet corner of the cosmos, relatively free of Quark Nova risks, simply because such regions are the only ones where complex life has time to evolve? Looking forward, our ability to detect and study Quark Novae will improve dramatically with next-generation observatories. The Vera Rubin Observatory, with its rapid wide-field sky surveys, will be able to catch transient events like double-peak supernovae in near real time. The James Webb Space Telescope, JWST, while optimized for infrared observations of early galaxies, may also provide critical data on distant SLSNA that could be Quark Nova candidates. Gravitational wave observatories like LIGO, Virgo, and CAGRA are already sensitive enough to detect neutron star mergers, and upgrades will make them increasingly capable of capturing the unique signatures of phase transitions within collapsing stellar cores. Meanwhile, ground-based experiments like the Large Hadron Collider, LHC, are pushing the boundaries of QCD and exploring the behavior of matter at extreme densities and temperatures. Though they can't replicate the conditions inside a neutron star, they can refine our understanding of the strong nuclear force, the force that binds quarks together, and help predict what might happen when those bonds break. The synergy between theoretical physics, astrophysical observation, and particle experiments is more critical than ever in the search for Quark Novae. In addition to these avenues, cosmic ray detectors are keeping watch for strangelets, tiny fragments of strange quark matter that may have escaped from quark stars. If strangelets exist and are stable, their detection would be a smoking gun for the existence of quark matter outside laboratory conditions. Even one confirmed strangelet event would revolutionize particle physics and cosmology. Projects like AMS-02 and ground-based detectors like the Pierre Auger Observatory are on the lookout, patiently sifting through cosmic noise for a glimpse of the strange. As we press onward, new questions emerge. Could quark stars be magnetars? These ultramagnetic neutron stars spin rapidly and emit intense bursts of X-rays and gamma rays. If the magnetic field structures of quark stars differ from those of neutron stars, perhaps due to the superconducting nature of quark matter, this could provide a unique electromagnetic fingerprint. Or perhaps the extreme rigidity of quark stars allows them to undergo starquakes more violently than neutron stars, releasing sudden pulses of energy that we can detect as fast radio bursts, FRBs. Some researchers even suggest that certain FRBs, those mysterious millisecond-long flashes of radio waves from distant galaxies, could be explained by crust cracking on a quark star. In this scenario, a strain builds up in the ultra-dense quark matter until it snaps, releasing an intense burst of radiation. The idea is still in its infancy, but it illustrates how Quark Novae and their aftermaths are infiltrating discussions across every domain of astrophysics. In this deepening view of cosmic transformation, we begin to appreciate that Quark Novae may not just be isolated astronomical events, but rather central nodes in the grand latticework of universal change, events that both end and begin, that destroy and create, and that offer profound insights into the boundaries of known physics. Each possibility they open teases the limits of our current understanding, urging scientists to reconsider long-standing assumptions about the very nature of matter, energy, and time. One of the most profound implications of Quark Novae lies in their potential role in reshaping the so-called nuclear landscape, the map of all possible configurations of protons and neutrons within atomic nuclei. Under normal circumstances, this landscape is well behaved, with nuclei becoming increasingly unstable beyond certain numbers of neutrons or protons. But in the environment of a quark nova, where conditions push matter beyond these limits, new exotic nuclear states might arise, states that can only exist for fractions of a second before dissolving into quark matter or ejecting massive amounts of radiation. The detritus of such events, the remnants cast off into interstellar space, could carry with them the signatures of these novel configurations. Isotopes never seen on Earth, but theoretically possible, could drift in the quark nova winds. These hyper-rich isotopes might hold clues not only to the event that spawned them but also to new physics beyond the standard model. If we could one day detect and isolate them in cosmic dust or meteorite samples, they could serve as direct evidence of quark nova nucleosynthesis, cementing the phenomenon not just in theory but in cosmic archaeology. On a macro scale, the gravitational impact of a quark nova cannot be overstated. Although the mass involved may be just a few solar masses, the concentration and release of energy during the quark deconfinement transition are truly stupendous. This sudden rearrangement of mass and pressure can send ripples through spacetime, gravitational waves that carry a clean, unscattered signal of the violent inner workings of a collapsing core. Unlike electromagnetic waves, which can be absorbed, re-emitted, or scattered, gravitational waves travel undisturbed, a pristine message from the depths of stellar collapse. If detected, these gravitational wave patterns could have unique features: a brief delay after the initial supernova, a secondary high-frequency burst tied to the moment of quark formation, or a tapering tail indicating strange quark matter stabilization. These signals would differ from black hole mergers or binary neutron-star collisions and could provide an unambiguous signature of a quark nova. From this perspective, observatories like LIGO, Virgo, and CAGRA become time machines and stethoscopes, listening to the very heartbeat of dying stars and capturing the seismic quakes that accompany the birth of exotic matter. Future detectors like the Einstein telescope or LISA may provide the sensitivity needed to catch even subtler features of these stellar transitions. Meanwhile, back in the realm of theory, the equation of state, EOS, for quark matter remains one of the most hotly debated and deeply studied aspects of high-energy astrophysics. The EOS describes how pressure relates to density and temperature in a given type of matter. For ordinary gases or even degenerate stellar cores, these relationships are relatively well known. But for quark matter, the variables are extreme. Quantum chromodynamics, QCD, the theory that governs the strong nuclear force, is incredibly complex at high densities and low temperatures, precisely the conditions found in a collapsing neutron star. Multiple models have emerged. Some predict a sharp first-order phase transition, where the matter snaps from hadronic to quark states like water boiling into steam. Others propose a more gradual crossover, especially at slightly lower densities, where mixed phases may coexist, so-called pasta phases, with interpenetrating regions of nucleons and quarks. The presence or absence of such phases has huge implications for the kind of energy a quark nova would release and the specific observational features it might produce. Still other models propose the formation of color superconductors, a bizarre and beautiful state where quarks pair up similarly to electrons in superconductors, leading to frictionless flow and new magnetic behaviors. In such states, the matter inside a quark star could conduct electrical and thermal energy with unprecedented efficiency, altering how the remnant cools and interacts with magnetic fields. If we could ever directly observe such a color superconducting core, or even infer its presence from a strange cooling rate or an unusual magnetic signature, it would confirm not only the existence of quark stars but also an entire class of matter that has never been created in laboratories on Earth. Even the magnetic structure of such objects challenges our understanding. A neutron star is already immensely magnetic, but a quark star, especially a rapidly rotating one with color superconducting properties, could sustain exotic field geometries. These configurations might produce rare electromagnetic phenomena, such as highly polarized emissions, twisted magnetospheres, or even cyclic outbursts triggered by internal magnetic reconnection events. If such emissions were detected and matched with theoretical predictions, it could open an entirely new subfield of astronomy, magnetoquark star astrophysics. And then, there is the possible connection to dark matter. Some researchers speculate that quark matter, if absolutely stable and capable of forming compact chunks or nuggets, could contribute to the dark matter content of the universe. Unlike weakly interacting particles, these nuggets would be heavy, rare, and almost undetectable by traditional means. Yet if they formed in the aftermath of early universe Quark Novae, or during the Big Bang's own phase transitions, they could still be drifting silently through the cosmos, hidden among the stars, influencing galactic rotation curves and lensing patterns with their mass. In this speculative yet tantalizing vision, Quark Novae are not just curiosities of dying stars. They are architects of structure, sources of gravitational echoes, creators of heavy elements, generators of exotic particles, and maybe even contributors to the invisible mass of the universe. They are keys to unlocking both the deepest interior of matter and the vastest scale of cosmic architecture. Their rarity, if real, makes them all the more precious. In the cosmos, it is often the rare events that teach us the most, the black swans that reveal hidden rules. Just as pulsars transformed our understanding of compact objects, and as gravitational waves opened a new window on the universe, so too could the confirmed discovery of a quark nova redefine what we believe is possible when matter collapses. And it is precisely this promise that drives researchers forward. The universe does not reveal its secrets easily, but the trails are there, in spectra too bright, in bursts too strange, in masses too heavy, and in theoretical models that whisper of another layer just beneath the surface. Somewhere out there, a neutron star is nearing its critical density. Quarks are twitching within its core, nearing a collective decision to break free. When they do, they will rewrite not just the fate of that star, but perhaps our understanding of the universe itself. The transformation from neutron matter to quark matter, deep in the interior of a collapsing star, is not just a physical process, it is a profound phase transition that alters the identity of matter itself. The boundaries between particles dissolve. The distinction between neutrons and protons vanishes. The very framework that once held quarks bound within nucleons disintegrates under the unbearable pressure, and a new regime of matter emerges, pure, deconfined, and ferociously dense. In such moments, nature enacts a process that no particle accelerator on Earth has yet achieved. While the Large Hadron Collider can recreate conditions close to the early universe for a fleeting instant, only the core of a quark nova sustains those extremes long enough, and at the required densities, to push past the limits of confinement. This makes every quark nova not just a cataclysmic event but a laboratory, a natural collider writing its results into space, waiting for distant observers to read the signs in the starlight. Even the crust of the star plays a role in this violent transformation. In some scenarios, the outer neutron star layers are ejected with tremendous force when the core transitions into a quark star. This ejection is not like the gentle solar winds of a main sequence star, nor even the expanding shell of a classic supernova. This is more akin to a fragmentation. The sudden loss of pressure support inside, combined with an intense release of latent energy, can blast the crust into space at relativistic speeds. It becomes a storm of neutrons, protons, heavy nuclei, and perhaps even strangelets, hypothetical particles composed of stable combinations of up, down, and strange quarks. If strangelets exist and are stable, they could seed further transformations. The so-called strange matter hypothesis suggests that if a strangelet were to collide with ordinary nuclear matter, it might catalyze a chain reaction, converting everything it touches into more strange matter. While this idea remains theoretical and somewhat controversial, it adds another layer of urgency and curiosity to Quark Nova research. Could such particles spread through space? Could they fall to Earth, undetected, their interactions too rare to notice? Or could they someday become tools for energy generation or probes of extreme physics? But let us return to the moment of explosion, to that instant when quarks first break free. In that singular moment, a quantum-level phenomenon becomes macroscopic. It is as though the vacuum structure of space-time itself has shifted. The gravitational well deepens, perhaps even briefly forming a quasi-black hole before the repulsive pressure of quark degeneracy halts the collapse. A pulse of gamma rays might burst forth, not from surface magnetic field realignment like in a magnetar flare, but from the raw thermodynamic fury of a new phase of matter being born. And in the minutes and hours that follow, as the newborn quark star cools, it shines not with the steady glow of a cooling white dwarf, but with ghostly neutrino winds and flickering X-rays, emissions that whisper of processes far beneath the surface. The landscape of such an event is chaotic. The expelled crust races away, ionized and radioactive. Shock fronts crash into interstellar gas, lighting up regions of space with complex emissions that may mimic or outshine regular supernova remnants. This can make detection challenging. For years, astronomers may classify such events under broader categories: peculiar type IB/C supernovae, fast blue optical transients, or even long gamma-ray bursts with no known progenitor. But beneath these labels may lie a small, rare breed of cosmic explosions, a breed powered not by fusion, but by quark deconfinement. These potential signals are being hunted. Researchers now comb through sky survey data, reanalyzing transients with unusually short durations, extreme brightness, or inexplicable delay patterns. One such candidate is SN 2006 GY, an extraordinarily luminous supernova that defied previous energy models. Though not confirmed, it sparked interest in whether such high luminosity might be explained by a quark nova occurring within a massive star's envelope, leading to a double explosion mechanism. In such a case, the first explosion, a conventional supernova, weakens the outer shell, and the second, the Quark Nova, slams into it with delayed ferocity, lighting it up from within. This dual shock model is elegant, and its implications are staggering. It suggests that the full death of a massive star might not be a single event, but a layered detonation, a celestial echo of thermonuclear devices on Earth, where a fission bomb triggers a fusion one. In this analogy, the fusion stage corresponds to the traditional supernova, while the secondary, more powerful detonation, the Quark Nova, takes over to release orders of magnitude more energy. It also implies that our current models of stellar evolution may be incomplete. Stars might not just become white dwarfs, neutron stars, or black holes. There may be a whole hidden population of quark stars masquerading in the data. Some might appear as neutron stars with inexplicable masses. Others might appear as cooling remnants with strange light curves or magnetic behaviors. A few might remain completely dark, compact, cold, and almost invisible save for their gravitational fingerprint. And speaking of gravity, consider the orbital systems that might form if a quark nova occurs in a binary. If one member of a binary system undergoes a quark nova, the effects on its companion can be dramatic. If the companion is a white dwarf, the impact could trigger a type I supernova. If the companion is a neutron star or black hole, gravitational interactions could fling both objects into deep space, or bring them into spiraling doom, culminating in further mergers that seed even heavier elements and more gravitational waves. One could imagine an exotic stellar genealogy. A massive star collapses into a neutron star. The neutron star cools and accretes matter until it hits the quark threshold and detonates in a quark nova. The remnant is a quark star. That quark star, still in a binary, later merges with a companion and collapses entirely into a black hole. In this life cycle, a single object has passed through 4 or 5 distinct stellar phases, each one exotic, each one a laboratory for extremes of physics, and each one leaving its fingerprint on the universe. The breadth of potential research arising from this single type of event is staggering. From nuclear physics to cosmology, from gravitational wave astronomy to high-energy neutrino detection, the Quark Nova touches every domain. It challenges the completeness of the periodic table. It tests the limits of general relativity. It pressures quantum chromodynamics to prove itself in regimes it was never built to handle. And we are just beginning. Somewhere deep in the sky, in a patch of darkness pierced by 1,000 specks of light, a star is collapsing, not silently, but invisibly. We may not see the first signals for hours, perhaps days. But when we do, they will come with fury, a sudden flash, a rare isotope in a meteorite, a hiccup in a pulsar's spin rate, or a gravitational ripple that bends the silence of space. And when those signs arrive, we will decode them, not just to confirm a theory, but to glimpse the true, untamed power of matter at its breaking point. As we look deeper into the cosmic landscape, it becomes increasingly apparent that the study of Quark Novae could revolutionize our understanding of the universe. A Quark Nova isn't just a stellar death. It's an extraordinary event that combines the complexities of gravity, matter, and quantum forces into a singular occurrence that might hold the keys to some of the most profound mysteries of modern physics. The mystery lies in its rarity, and in the potential to learn not just about dying stars, but about the very nature of matter itself. We know that stars are not simply burning fuel, they are waging a constant battle against gravity. The pressure at the core of a dying star creates a kind of self-sustaining furnace, where hydrogen atoms fuse into heavier elements. But when the fuel is exhausted, and the star can no longer maintain this balance, something dramatic must happen. For typical stars, this results in a supernova, and if the mass is sufficient, the remnant can become a black hole or a neutron star. But when the conditions are just right, when the star has enough mass to collapse beyond a neutron star's density, then a Quark Nova is born. The key to understanding Quark Novae lies in grasping the state of matter in extreme environments. We are accustomed to thinking of atoms as the fundamental building blocks of matter. But at the core of a dying star, we enter a realm where atoms break down into their constituent particles, protons, neutrons, and electrons. However, in a Quark Nova, even the neutrons and protons cannot hold their structure against the extreme gravitational forces. The neutrons themselves are crushed to their constituent quarks, up, down, and possibly strange quarks, and thus, we enter the domain of quark matter. One of the most challenging aspects of Quark Novae research is the uncertainty around the nature of quark matter. This matter, which could be in a strange form, often referred to as strange quark matter, is theorized to be a more stable phase of matter than ordinary nuclear matter. In this phase, quarks are no longer confined inside hadrons but instead move freely in a superfluid-like state. This has profound implications for the stability of a quark star. Unlike a neutron star, which is supported by neutron degeneracy pressure, a quark star would be held up by the degeneracy pressure of quarks. But whether this kind of matter is stable over long periods is still a matter of debate. Some models predict that a quark star would be incredibly stable, while others suggest that strange matter might decay into ordinary matter if it encounters it, possibly releasing vast amounts of energy in the process. To answer these questions, astronomers must rely on indirect methods of observation. Quark novae are incredibly difficult to detect directly due to their fleeting and high-energy nature. Their potential signatures might include unusual bursts of gamma rays, gravitational wave signals, and oddities in the light curves of certain supernovae. The detection of strange quark matter might come not in the form of a direct image or even a visible explosion, but rather through its effects on the surrounding environment, anomalous accelerations, a shift in the expected temperature and density profiles of the remnants, or unexpected patterns in the way radiation travels through space. Interestingly, the study of Quark novae might shed light on another unsolved mystery of the cosmos: the nature of dark matter. Many scientists believe that dark matter consists of particles that interact weakly with regular matter, and some have even suggested that strange matter could be a candidate for dark matter. If Quark novae can produce an ejected strange matter, this could offer an entirely new way of looking for dark matter. Rather than searching for weakly interacting massive particles, WIMPs, or axions, we might find clues in the remnants of Quark novae, strangelets or strange quark matter that could be spread out across the universe. quietly interacting with its environment in ways we have yet to fully comprehend. Even though Quark Novae are rare events, their discovery would be a monumental achievement, pushing our understanding of astrophysics and high-energy particle physics. They are a bridge between the behavior of matter under extreme gravitational forces and the strange world of quantum chromodynamics, the theory that governs the interactions of quarks and gluons. The implications of studying Quark Novae extend far beyond just astrophysics. They could offer insights into the fundamental forces of nature and the very fabric of the universe itself. The quest to detect and understand Quark Novae involves the most sophisticated technology available. For example, astronomers might use a combination of gravitational wave detectors, which can pick up the subtle vibrations in space caused by the collapse of massive objects, and gamma-ray telescopes, which can capture the high-energy radiation emitted by violent events like supernovae or Quark Novae. Space-based observatories such as the Laser Interferometer Gravitational Wave Observatory, LIGO, and the European Space Agency's XMM Newton telescope are some of the most powerful tools in the search for these elusive events. But even with the best instruments, the challenge remains in finding clear evidence of a quark nova. Unlike more conventional supernovae, Quark Novae are so short-lived and energetically distinct that their detection requires highly sensitive equipment capable of picking up the faintest of signals from the farthest reaches of space. Despite these challenges, the theoretical groundwork for identifying Quark Novae is being laid through simulations and computer models. By understanding the expected physical properties of quark stars, scientists are developing better models for how these objects would behave in different astrophysical environments. These models take into account the complex interplay between gravity, thermodynamics, quantum chromodynamics, and general relativity, which is crucial for predicting the outcomes of stellar collapse. These models also help astronomers refine their search criteria for potential quark nova candidates and improve the analysis of observed supernova remnants. In many ways, the study of Quark Novae represents a convergence of multiple disciplines, from particle physics to cosmology, from theoretical models to practical observation. As we push the boundaries of our knowledge, we will undoubtedly encounter new and surprising phenomena that challenge our preconceived notions of how matter behaves under the most extreme conditions. Perhaps in the future, the study of Quark Novae will become a cornerstone of modern astrophysics, a bridge between the macroscopic world of stars and the microscopic world of fundamental particles. The mysteries surrounding Quark Novae are far from solved, and each discovery in this field opens up new avenues for exploration. Just as the discovery of neutron stars and black holes revolutionized our understanding of stellar evolution and the fundamental nature of matter, the eventual detection and study of Quark Novae will undoubtedly expand our understanding of the universe and our place within it. The universe is a vast, complex, and mysterious place, and events like Quark Novae are reminders of just how much there is yet to discover. The search for Quark Novae and the study of their physical properties will challenge not only our understanding of the universe but also our fundamental assumptions about the behavior of matter and the laws of physics. It will be a reminder that the cosmos is full of unexpected wonders, each one waiting to be uncovered by the relentless curiosity of humankind. The search for Quark Novae has profound implications, not only for astrophysics but also for our broader understanding of the universe. One of the most fascinating questions raised by the potential existence of Quark Novae is what they might teach us about the creation and behavior of matter in the most extreme environments. We know that under normal conditions, matter is structured around atoms, which themselves consist of protons, neutrons, and electrons. However, when subjected to extreme pressures and temperatures, the atomic structure begins to break down, and the universe reveals its most fundamental building blocks, quarks. Quarks, as we know, are the elementary particles that form protons and neutrons, and when matter is crushed under the immense gravity of a collapsing star, these quarks may become unbound from their hadrons, protons and neutrons, and enter a new phase of matter. This state of matter, sometimes referred to as quark-gluon plasma, is theorized to exist in the hearts of Quark Novae. It represents a phase of matter where quarks are no longer confined to particles but are instead free-moving, potentially altering our understanding of the strong force, which binds quarks together. Theoretical models predict that during a quark nova, as a collapsing star undergoes a transition from a neutron star to a quark star, a violent release of energy could occur. This energy release might be detectable in various forms, including high-energy gamma rays, neutrinos, and gravitational waves. The specific signatures of a quark nova could be a smoking gun for scientists searching for the elusive conformation of strange quark matter. However, detecting such events is far from easy, as the phenomena would occur on scales that are difficult to observe with current technologies. That being said, advancements in detectors such as gravitational wave observatories like LIGO and space telescopes might eventually uncover clues hidden in the remnants of these rare, explosive occurrences. We also have to take into account the unique properties of quark matter itself. This exotic form of matter is speculated to have a different density and behavior from the familiar forms of matter we encounter in our everyday lives. One of the most intriguing questions about quark matter concerns its stability. Is strange quark matter stable over long periods? Or is it merely a fleeting phase that decays into regular matter after a short time? Some theories suggest that quark matter could be more stable than ordinary nuclear matter, potentially making it a candidate for dark matter. If strange quark matter is indeed stable, we might have stumbled upon a new form of matter that could help explain one of the greatest unsolved mysteries in cosmology: the nature of dark matter. Dark matter, which accounts for approximately 85% of the total mass of the universe, is invisible to traditional forms of detection, such as electromagnetic radiation. Scientists have only inferred its existence through its gravitational effects on visible matter. If Quark Novae produce strange quark matter, then these events might represent an opportunity to identify dark matter indirectly. Some scientists speculate that strange matter, which could be produced during a quark nova, might be scattered throughout the universe, undetectable by most instruments, but exerting its influence on the gravitational fabric of space-time. If Quark Novae could indeed contribute to the population of strange matter in the universe, it would provide us with an entirely new way to study dark matter. This connection could also potentially explain some of the more puzzling observations in cosmology, such as the unexpected way galaxies rotate or the behavior of galaxy clusters. Strange matter, formed from Quark Novae, might interact with regular matter in ways that we are only beginning to understand. These interactions could lead to new breakthroughs in our understanding of the universe's structure and composition. In addition to the implications for dark matter, the study of Quark Novae could also offer insights into the origins of heavy elements in the universe. We already know that supernovae are responsible for creating many of the heavy elements we observe on Earth, such as gold, platinum, and uranium. However, Quark Novae, with their extreme conditions and energetic explosions, could play a significant role in the synthesis of even heavier elements, possibly even those that exist beyond the current periodic table. This opens up fascinating possibilities for understanding the chemical evolution of the universe and the processes that lead to the formation of the elements we find in the stars, planets, and life forms on Earth. Moreover, understanding Quark Novae could enhance our knowledge of fundamental physics, particularly quantum chromodynamics, QCD, the theory that describes the strong interaction between quarks and gluons. QCD is one of the cornerstones of the Standard Model of particle physics, but it is notoriously difficult to study directly because quarks and gluons are confined within hadrons under normal conditions. In a quark nova, however, the high temperatures and pressures could provide an environment where quarks are free to interact in ways that are normally impossible to observe. By studying the aftermath of a quark nova, scientists could gain valuable insights into the fundamental forces that govern the universe. While quark novae remain a theoretical phenomenon for now, the search for them is an exciting frontier in both astrophysics and particle physics. As technology advances, it is possible that new observational techniques will allow us to probe these extreme events more directly. With the advent of next-generation telescopes, advanced particle detectors, and improved gravitational wave observatories, we may soon be in a position to detect the faint signals of a quark nova and confirm its existence. Such a discovery would be a monumental achievement, providing us with a new window into the most extreme conditions of the universe and opening up new avenues of exploration in fundamental physics. In the context of the broader universe, quark novae represent more than just a peculiar astrophysical event. They are a glimpse into the very nature of matter, space, and time. If strange quark matter exists, and if Quark Novae are responsible for creating and ejecting this matter, we may be witnessing one of the most fundamental processes that govern the evolution of the cosmos. The potential to uncover a new form of matter, explore the mysteries of dark matter, and deepen our understanding of the fundamental forces of nature is what makes Quark Novae such a compelling subject of study. For centuries, astronomers have looked to the stars to unlock the mysteries of the universe, and Quark Novae represent the next frontier in this quest. As we continue to explore the extreme environments of collapsing stars, the behavior of matter under immense gravitational forces, and the interactions between quarks and gluons, we are not just pushing the boundaries of astrophysics. We are also exploring the very fabric of the universe itself, seeking answers to the most profound questions about the nature of matter, the origin of dark matter, and the ultimate fate of the stars. The potential discovery of Quark Novae is still a few steps ahead in the future, but as our technological and theoretical capabilities continue to evolve, the likelihood of witnessing such an event becomes increasingly possible. What we learn from these explosive phenomena could reshape our understanding of the cosmos, providing new insights into everything from the formation of galaxies to the behavior of the most fundamental building blocks of matter. In the end, Quark Novae may be one of the many mysteries that remind us how little we truly know about the universe, and how much more there is to discover. As we venture deeper into the theoretical underpinnings of Quark Novae, it's important to consider the role that these phenomena might play in the life cycle of stars. To fully appreciate the potential significance of a quark nova, we must first acknowledge the extreme conditions under which these events occur, specifically the nature of neutron stars and their evolution. Neutron stars themselves are already some of the densest objects in the universe, formed when a massive star exhausts its nuclear fuel and undergoes a supernova explosion. The remnant core left behind is primarily composed of neutrons, which are densely packed together, creating an object with incredible gravitational pull and density. At this stage, gravity is so strong that even atomic nuclei are crushed into their constituent neutrons. These neutron stars can have masses greater than that of the Sun, yet their diameters may only span around 10 to 20 kilometers. Despite their intense density, however, neutron stars are still composed of baryonic matter, the same type of matter that makes up everything we are familiar with in the universe. But what happens when the pressure inside a neutron star continues to increase, exceeding the stability of the neutrons themselves? This is where the possibility of Quark Novae arises. Under these extreme conditions, theorists speculate that neutrons may break apart into their constituent quarks, specifically, up quarks, down quarks, and the heavier strange quarks. When this happens, a quark star could form, a new phase of matter that exists at even higher densities than neutron stars. These quark stars could potentially be the progenitors of Quark Novae. A quark nova, then, could be the violent explosion that occurs when a quark star undergoes a catastrophic release of energy, possibly triggered by a sudden instability within the quark matter itself. In the context of stellar evolution, this could represent the final stage of a star's collapse. Whereas a supernova marks the death of a normal star and a neutron star marks the birth of an ultradense remnant, a quark nova might signal the end of a neutron star's life, as it transitions into a more exotic state of matter. This transition could lead to the creation of a more compact and extreme object, potentially opening the door to the possibility of strange matter existing independently of its parent star. In considering the mechanics of a quark nova, it is essential to recognize the energy scales involved. The gravitational collapse of a massive star can unleash an immense amount of energy, and in the case of a quark nova, this energy would likely be far more concentrated than anything seen in typical supernovae. As quarks undergo a phase transition, the energy released could be enough to momentarily disrupt the delicate balance of forces that govern the behavior of matter at the subatomic level. Such an explosion could send shockwaves throughout space, potentially sending particles like neutrinos and gamma rays in all directions, observable by even the most distant telescopes. This violent event could be powerful enough to rival, or even exceed the energy released during a typical supernova, making it a truly unique event in the life cycle of stars. One of the key questions surrounding Quark Novae is the exact nature of the energy release and its observability. If Quark Novae are real, they could produce a distinctive signature in the electromagnetic spectrum. High-energy gamma rays, for instance, are known to be associated with high-energy astrophysical events such as supernovae, black hole accretion, and pulsar emissions. A quark nova, with its extreme conditions, could produce even more intense gamma-ray bursts. These bursts might offer the first direct evidence of quark matter beyond the confines of experimental particle accelerators, providing us with a rare glimpse into the most fundamental aspects of matter itself. In addition to gamma rays, Quark Novae could also emit large quantities of neutrinos. Neutrinos are subatomic particles that rarely interact with ordinary matter, making them incredibly difficult to detect. However, because they are produced in vast quantities during the collapse of a star, they could offer a secondary signal of a quark nova event. Specialized neutrino detectors, such as those buried deep underground to shield them from other forms of radiation, could potentially pick up these elusive particles, allowing us to probe the interior of a quark nova and gain further insight into the high-energy processes that occur within these exotic stars. The role of quark novae in the greater cosmic landscape is not limited to their potential to shed light on dark matter or provide clues about the strong force. They could also play a crucial role in the synthesis of heavy elements. As previously mentioned, supernovae are responsible for the creation of many of the heavy elements that populate our universe, such as gold, platinum, and uranium. However, the energy released in a quark nova could result in even more exotic processes, potentially creating new types of heavy elements that have never been seen before. These elements might exist only in the brief moments following a quark nova, as the extreme conditions dissipate and the remnants of the star begin to cool. The potential for quark novae to contribute to the production of new and unknown elements is not just a fascinating theoretical question. It could have profound implications for our understanding of the chemical evolution of the universe. Could quark novae be responsible for elements heavier than uranium? Could they produce a new class of exotic matter that defies conventional chemical classification? These questions are yet to be answered, but the possibility of discovering entirely new elements or forms of matter would be a thrilling discovery that could reshape the periodic table as we know it. In considering the observational challenges posed by quark novae, it is important to keep in mind the rarity of such events. If quark novae are indeed a real phenomenon, they would likely be extremely rare occurrences in the cosmos. Given the vast distances between stars and the fact that most neutron stars are located in distant galaxies, observing a quark nova directly would be a challenging task. Nonetheless, the rise of more advanced observational instruments may make it possible to detect even these rare events. For instance, next-generation space telescopes and observatories, such as the James Webb Space Telescope, could potentially offer the sensitivity required to detect the faint electromagnetic signatures of a quark nova. Similarly, more sensitive gravitational wave detectors, such as the planned LISA, Laser Interferometer Space Antenna, mission, could allow us to detect the gravitational waves produced by the collapse of a neutron star into a quark star, offering another potential avenue for identifying these elusive events. In the future, the combination of high-energy astrophysical surveys, neutrino detectors, and gravitational wave observatories could provide us with the tools needed to observe quark novae and confirm their existence. With advances in theoretical modeling, we may also gain a better understanding of the detailed physical processes that occur during these events, shedding light on the transition from neutron star to quark star and the nature of strange matter. The discovery of quark novae would not only deepen our understanding of stellar evolution, but it would also contribute to the broader field of cosmology. Understanding how extreme states of matter behave in the most extreme environments could help us unravel the mysteries of the early universe, where similar conditions may have existed just moments after the Big Bang. By studying quark novae, we might gain insights into the very conditions that led to the formation of the universe itself. As we continue to explore the outer reaches of the universe and investigate the most extreme environments, quark novae stand as a tantalizing reminder of the vast unknowns that still lie ahead. While much about them remains theoretical, the potential to uncover new forms of matter, probe the mysteries of dark matter, and expand our understanding of the fundamental forces of nature makes them a subject of great intrigue. The search for Quark Novae represents a quest for answers to some of the most profound questions in science, and as our understanding of the universe continues to evolve, so too will our quest to uncover the secrets hidden within these extraordinary cosmic events. The search for Quark Novae also opens up the possibility of understanding more about the fundamental forces and particles that govern our universe. These events could provide a unique laboratory for studying the behavior of quarks in environments where gravity, pressure, and temperature are so extreme that they push the very limits of our current understanding of physics. The transition from a neutron star to a quark star, and the subsequent Quark Nova explosion, could represent the ultimate test for theories related to quantum chromodynamics, QCD, which describes the strong force responsible for holding quarks together within protons and neutrons. One of the most exciting aspects of Quark Novae is the potential to observe and study strange quarks. In everyday matter, quarks exist in three types: up, down, and charm. However, in high-energy environments, such as those found inside a quark nova, we may see the emergence of strange quarks. Strange quarks are heavier and more unstable than up and down quarks, and their presence would mark the formation of strange matter, an exotic state of matter that has never been observed in nature outside of high-energy particle accelerators. Strange matter, consisting of up, down, and strange quarks, could theoretically be more stable than ordinary matter under certain conditions, though it remains highly speculative. If Quark Novae are indeed real, the creation and study of strange matter could have profound implications for our understanding of both nuclear physics and the very nature of matter itself. Understanding the properties of strange quarks and strange matter could reveal new insights into how the universe behaves at its most fundamental level. Another critical question that arises in the study of Quark Novae is the role that they could play in the formation of black holes. As previously mentioned, neutron stars are already incredibly dense objects, and when they collapse further, they can become black holes. However, if a quark nova were to occur, releasing a tremendous amount of energy, could it trigger the formation of a black hole in the process? This remains a point of speculation in the scientific community, as the dynamics of quark stars are not yet fully understood. One hypothesis is that the collapse of a quark star could lead to the formation of a black hole, as the object's density and gravitational pull would increase dramatically during the collapse. However, the outcome could also depend on the amount of energy released during the quark nova. If the explosion is powerful enough, it might prevent the collapse from forming a black hole, leading to the ejection of material instead. Alternatively, the formation of a black hole could occur as a result of a quark nova's violent explosion, adding another layer of complexity to the process. In terms of observational implications, Quark Novae could provide a new avenue for testing general relativity and our understanding of gravitational collapse. The intense gravitational fields around quark stars and the potential for black hole formation would provide an ideal setting for studying how matter behaves under extreme conditions, potentially revealing new aspects of spacetime and gravity. Observing the aftermath of a quark nova, particularly in terms of gravitational waves, could offer valuable insights into the physics of these exotic objects. The detection of gravitational waves from a quark nova event would be an exciting breakthrough in astrophysics. Gravitational waves are ripples in the fabric of spacetime that are produced by the acceleration of massive objects, such as merging black holes or neutron stars. In the case of a quark nova, the collapse of a neutron star into a quark star, or the subsequent explosion, could produce gravitational waves that could be detected by observatories such as LIGO, Laser Interferometer Gravitational Wave Observatory, or Virgo. By analyzing these waves, scientists could gain a deeper understanding of the inner workings of quark stars and the dynamics of these powerful events. Moreover, Quark Novae could help shed light on the role of these exotic phenomena in the broader context of galactic evolution. Many of the heaviest elements in the universe, including gold and platinum, are believed to be created in the aftermath of supernovae and other catastrophic stellar events. However, as we have discussed, Quark Novae could lead to the creation of even more exotic elements that would not be possible in more conventional stellar explosions. By studying the remnants of Quark Novae, scientists may be able to better understand the process of nucleosynthesis and the formation of elements in the universe, potentially providing us with a deeper understanding of how galaxies and star systems evolve over time. Furthermore, the discovery of Quark Novae could have far-reaching implications for cosmology. As we look to the distant past, Quark Novae may offer clues about the early stages of the universe. During the first moments after the Big Bang, the universe was in an extremely hot and dense state, and quarks were free to move independently before combining to form protons and neutrons. By studying Quark Novae, we might gain insights into the conditions that existed during this primordial epoch and how the universe transitioned from a quark gluon plasma to the matter we see today. In addition to their potential to inform our understanding of the early universe, Quark Novae could also provide a unique perspective on the future of the cosmos. As the universe continues to expand, the density of matter will decrease, and stars will burn out. The end stages of stellar evolution will become increasingly dominated by these exotic objects, such as neutron stars, quark stars, and black holes. Quark Novae could play a crucial role in this cosmic evolution, providing a mechanism through which new forms of matter and energy are created. This could have profound implications for the ultimate fate of the universe, offering insights into the processes that will govern the cosmos in the distant future. The theoretical nature of Quark Novae has sparked much debate among scientists, and there is still much to be learned about their existence and properties. While the idea of quark stars and Quark Novae is still in the realm of speculation, it is possible that future discoveries will confirm their existence and provide us with a new window into the most extreme conditions in the universe. As observational technology continues to advance, and as our understanding of quantum physics, general relativity, and astrophysics deepens, Quark Novae may one day emerge as a key piece of the puzzle in our quest to understand the fundamental forces of nature. The concept of Quark Novae offers a fascinating glimpse into a new realm of astrophysics, where the boundaries of matter, energy, and gravity are pushed to their limits. These hypothetical events, born from the collapse of neutron stars into quark stars, could provide answers to some of the most profound questions in science. They hold the potential to reveal new forms of matter, test the limits of quantum chromodynamics, and help us better understand the complex processes that shape the universe. While we may still be far from observing a Quark Nova directly, the quest to understand these exotic events is one that could yield transformative discoveries, expanding our knowledge of the cosmos and the very nature of reality itself. The search for Quark Novae may also fuel advancements in the field of computational astrophysics, requiring the development of more sophisticated simulations and modeling techniques. Current models for neutron stars and black holes are complex and require high-performance computing to simulate the dynamics of such extreme environments. However, Quark Novae would push these models to even further extremes, challenging scientists to refine their understanding of how matter behaves under conditions of immense pressure and temperature. By simulating the formation and explosion of quark stars, researchers would be able to test a range of theories about the state of matter under such extreme conditions. For instance, they could explore how quark matter behaves when exposed to intense gravitational fields, or how it interacts with electromagnetic radiation in the aftermath of a quark nova. These simulations would also be essential in understanding the processes that occur during the collapse of a neutron star, potentially offering critical insights into the formation of black holes, gravitational wave signatures, and the emission of high-energy particles. The quest to understand Quark Novae may also have practical applications beyond theoretical astrophysics. For example, the study of extreme states of matter could have implications for nuclear fusion research. Understanding the behavior of quarks in dense environments could inspire new techniques for creating controlled fusion reactions here on Earth, possibly leading to breakthroughs in clean energy production. While this is still a speculative area of research, the potential for interdisciplinary applications of Quark Nova-related discoveries is immense. As scientists continue to refine their tools for observing the universe, the detection of Quark Novae may become a reality. With the advent of next-generation telescopes and observatories, such as the James Webb Space Telescope and the Square Kilometre Array, the potential for discovering and studying these events grows increasingly likely. These instruments are designed to probe deep into the cosmos, capturing light and radiation across the electromagnetic spectrum and potentially detecting the faint signals emitted by quark novae. One of the key challenges in observing quark novae is their potential rarity. Even if these events are relatively common in the broader universe, the specific conditions required for their detection, such as the exact alignment of gravitational waves or the presence of specific radiation signatures, may make them elusive to current observational techniques. However, the increasing sensitivity of detectors and advancements in astronomical instrumentation could one day make it possible to detect these events more easily, leading to breakthroughs in our understanding of the universe. One particularly exciting aspect of quark novae is their potential role in the broader context of stellar evolution and the end of life of massive stars. While much attention has been given to the formation of black holes from the collapse of massive stars, quark stars, if they exist, could provide an additional avenue for understanding how stars evolve in the final stages of their life cycles. The formation of a quark star through a supernova explosion could represent a fascinating alternative to the creation of black holes, opening up new pathways for the study of stellar remnants and their behavior under extreme conditions. Moreover, quark novae could offer crucial insights into the origins of cosmic rays, the high-energy particles that travel through space and bombard the Earth. These particles are believed to originate from sources such as supernovae, active galactic nuclei, and other high-energy astrophysical events. If quark novae are indeed real, they could represent yet another source of cosmic rays, with their explosive energy potentially producing vast amounts of high-energy particles that could be detected by ground-based observatories. The study of quark novae might also contribute to our understanding of the dark aspects of the universe. Much of the universe remains invisible to our current methods of observation, with dark matter and dark energy constituting the majority of its composition. While quark novae are not directly related to dark matter or dark energy, the insights gained from studying these events may inform our broader search for answers to the mysteries of dark energy, dark matter, and the fundamental forces of nature. In addition to advancing our understanding of the cosmos, quark novae could also serve as a tool for exploring some of the most profound philosophical questions about the universe. The study of quark stars and their potential to unlock the secrets of matter at its most fundamental level touches on questions about the nature of reality itself. What is the true nature of the universe's building blocks? How do the fundamental forces work together to shape the cosmos? The search for quark novae is not just a scientific quest, but a journey to the heart of the universe's mysteries, challenging our most fundamental assumptions about the fabric of reality. The potential discovery of quark novae also underscores the importance of scientific curiosity and exploration. As humanity ventures further into space and deepens its understanding of the universe, new questions will continue to emerge, pushing the boundaries of knowledge. The search for quark novae is a prime example of how the unknown can spark curiosity and drive innovation in ways we may never have imagined. Whether or not quark novae ultimately exist, the effort to understand them is a testament to the spirit of scientific inquiry and the relentless pursuit of knowledge. In the future, as we continue to observe the universe and gather data from increasingly sophisticated instruments, it is likely that quark novae, if they exist, will become a subject of intense study. In turn, these studies will illuminate new aspects of the universe, providing fresh insights into the extreme conditions that govern the behavior of matter and energy. Whether they are discovered in the near future or remain a theoretical concept for years to come, quark novae have the potential to expand our understanding of the cosmos and reveal some of its most profound secrets. The search for quark novae and the study of quark stars will likely remain one of the most exciting and enigmatic fields of astrophysics in the years to come. While we may not yet have definitive evidence of their existence, the ongoing research into these extraordinary objects is opening up new frontiers in our understanding of the universe. As our tools and techniques continue to evolve, quark novae may one day become a pivotal piece of the cosmic puzzle, offering answers to some of the deepest questions in science and physics. The study of quark novae represents the quest for knowledge at its most ambitious and transformative. By investigating these exotic and speculative phenomena, scientists are not only deepening our understanding of the cosmos, but also pushing the boundaries of human knowledge to explore the very fabric of reality. Whether or not quark novae ultimately exist, the pursuit of their study is a reflection of humanity's unyielding drive to understand the universe at its most fundamental level, a drive that will continue to shape the future of astrophysics for generations to come. The notion of quark novae also touches on a deep scientific principle, the idea that every major revolution in our understanding of the universe comes from challenging our assumptions about what is truly fundamental. Just as the concept of the atom was once considered indivisible until it was broken into subatomic particles, and those particles were in turn revealed to be composed of quarks, the possibility of quark novae challenges us to once again look deeper, to entertain the idea that even the densest objects we know, like neutron stars, might not be the ultimate endpoint in the collapse of matter. If neutron stars can collapse into quark stars and trigger quark novae, then what does that say about the nature of matter and the behavior of the strong nuclear force at extreme densities? Could there be states of matter beyond quark matter, forms we haven't even imagined yet? The hypothetical, preon models, for example, suggest that even quarks might be composed of more fundamental particles. If so, then quark novae might not be the final frontier, but merely another step down a long staircase into deeper layers of physical reality. This kind of speculation isn't just idle curiosity, it's precisely how science progresses. Historically, some of the most profound discoveries began with odd, unexplained anomalies that didn't fit within the known frameworks. Cosmic microwave background radiation was once a mysterious static. Neutrinos were once only theoretical patches to save conservation laws. Pulsars were mistaken for signals from alien civilizations. In each case, strange and elusive phenomena led to breakthroughs that reshaped entire fields of science. Quark novae may be one such enigma on the cusp of being unraveled. If we do manage to detect one, it would set off a cascade of research in multiple domains. Particle physicists would seize the opportunity to validate or refine their models of quantum chromodynamics under extreme conditions. Astronomers would revisit past transient events with new filters and perspectives. Cosmologists might begin recalibrating models of cosmic evolution if quark novae are found to have contributed significantly to metal enrichment or early structure formation in galaxies. Even the public imagination would likely be captivated by the discovery. Just as black holes and supernovae have become staples in science documentaries, books, and films, quark novae could become a new symbol of the universe's power and mystery. The idea that there are still explosions out there that dwarf the already unimaginable fury of a supernova would capture global attention, reinforcing the sense that our universe is far more dynamic, layered, and violent than we currently grasp. A confirmed quark nova would also trigger a hunt for the surviving objects it leaves behind, the elusive quark stars. These hypothetical stars would possess properties distinct from both neutron stars and black holes. They may have smaller radii for the same mass, possess different cooling patterns, or even generate unique magnetic field configurations. Their gravitational wave signatures might be slightly different, allowing researchers to fine-tune detection algorithms to pick out their signals in the noisy background of space. In turn, the identification of quark stars could help solve some long-standing mysteries in astrophysics. For instance, a number of compact stars observed so far don't quite fit within the expected mass-radius relationship for typical neutron stars. These outliers could very well be quark stars masquerading as neutron stars. With a confirmed quark nova model in hand, these ambiguous observations could be reinterpreted, possibly leading to the first catalog of known quark stars. Another captivating idea is the potential for quark novae to seed their surrounding environment with rare and exotic particles. Just as supernovae are responsible for enriching the interstellar medium with elements necessary for planet formation and life, quark novae might introduce entirely different kinds of particles or isotopes, ones that we haven't yet detected or fully understood. If any of these particles made their way to Earth, it could revolutionize particle detection and nuclear chemistry. It's even plausible that remnants of such events may already be buried in our planet's crust, waiting to be identified. Unusual isotopic ratios or unidentified high-mass nuclei in cosmic ray tracks could be relics of ancient quark novae that occurred in our galactic neighborhood. If so, future advances in geochemistry and particle physics could finally connect the dots between distant cosmic events and trace elements here on Earth, literally grounding the celestial in the terrestrial. Then there's the matter of the astrophysical environment surrounding Quark Novae. If one occurred in a binary star system, the ejected matter could interact with the companion star, possibly creating observable changes in its luminosity or spectral features. Alternatively, in dense stellar nurseries or globular clusters, a quark nova could produce shock waves that disrupt star formation, triggering or quenching nearby protostar development. These effects would ripple across entire regions of space, offering observable clues to researchers with the right tools and foresight. Furthermore, studying the distribution and frequency of quark novae across the observable universe could shed light on the broader evolution of galaxies and star populations. If they are more common in younger or metal-poor galaxies, that could inform models of stellar evolution under different initial conditions. If they occur frequently in certain mass ranges or spectral types of progenitor stars, this data could be used to refine our understanding of stellar life cycles and the statistical makeup of galactic populations. This line of research may also influence the way we think about the future of massive stars in our own galaxy. The Milky Way has numerous neutron stars scattered across its spiral arms, relics of past stellar deaths. If a portion of these neutron stars are slowly creeping toward the critical density required for a quark nova, then it's possible that our galaxy still has such events yet to unfold. Detecting even one would confirm decades of theoretical prediction and elevate the field of astrophysics to a new era of post-neutron star research. The possibility of observing a quark nova within our own galaxy, though rare, would be an event of global significance. Detectors across the electromagnetic spectrum would immediately turn their attention to it. Space-based telescopes would scan for gamma-ray bursts or unusual spectra, while gravitational wave detectors would analyze the signature of the collapse. Neutrino observatories deep underground would seek out the high-energy emissions from the core collapse, and cosmic ray detectors would scan for exotic particles arriving in Earth's atmosphere. It would be a coordinated, worldwide scientific event unlike anything previously witnessed. Even the possibility of using quark novae as standard candles in cosmology could emerge. If these events are found to have consistent and measurable properties, they might one day serve as tools to measure cosmic distances, much like Type Ia supernovae currently do. This could refine our estimates of the rate of cosmic expansion, or even provide new evidence in the debate over dark energy and the shape of the universe. In essence, the exploration of quark novae is a window into many of the deepest unsolved problems in physics and astronomy. From the behavior of matter at ultra-high densities, to the origins of heavy elements, to the birth and death of stars, and even the large-scale structure of the cosmos, quark novae touch nearly every aspect of modern astrophysics. And in doing so, they challenge us to expand our knowledge, sharpen our instruments, and rethink what we believe is possible in the vast and violent universe we call home. Quark novae not only present a theoretical marvel but also embody one of the few phenomena that might bridge the gap between particle physics and cosmology. They are a living laboratory of extremes, a fusion of forces and densities that challenge every known model of physics. For decades, scientists have tried to unify the four fundamental forces of nature: gravity, electromagnetism, the weak nuclear force, and the strong nuclear force, into one coherent framework. Quark novae exist in an environment where all four may interact in the most violent, unpredictable, and illuminating ways possible. The intense gravitational pull, the electromagnetic chaos of rotating magnetic fields, the weak interaction driving lepton emissions, and the dominant strong force orchestrating the behavior of quarks all clash and converge in this astrophysical crucible. This potential makes quark novae a candidate site for physics beyond the Standard Model. The Standard Model, despite its success in explaining particle interactions at everyday and collider-scale energies, falters at the edges, specifically when gravity is involved or when matter is compressed into forms far denser than atomic nuclei. In a quark nova, where the transition from hadronic to deconfined quark matter occurs at astronomical scales, we may find the cracks that will guide us toward new theories. These theories could include supersymmetry, quantum gravity, or even string theory frameworks, depending on what phenomena emerge from future observations. And we shouldn't overlook the possibilities raised by speculative but mathematically consistent models, such as those proposing extra dimensions. If additional spatial dimensions exist and are compactified or curled up at very small scales, then the extreme density of a quark nova could conceivably expose their influence, perhaps via gravitational anomalies or energy discrepancies in particle flows. Likewise, if dark matter interacts, however weakly, with baryonic matter, the quark nova's energy output and byproducts could serve as a diagnostic tool for detecting it. Even now, dark matter remains one of the universe's most elusive ingredients, and any new astrophysical phenomenon capable of offering insight into its properties would be transformative. This also brings up the tantalizing idea of quark novae as potential cosmic colliders. Much like the Large Hadron Collider smashes protons together to explore high-energy physics, quark novae might naturally replicate conditions far beyond what any Earth-based accelerator can achieve. For a fleeting moment, their inner regions might offer glimpses of what the universe looked like microseconds after the Big Bang: dense, hot, and rich in quark-gluon plasma. Observing or modeling such environments could help physicists refine cosmological models, test theories about baryogenesis, and even examine why the universe appears to be composed mostly of matter rather than antimatter. In the grand scheme of cosmic evolution, quark novae could have left permanent imprints on the structure of the universe itself. For instance, if a substantial number of quark novae occurred in the early universe, their combined energy release could have impacted the rate of reionization, heating of the intergalactic medium, or the timing of the formation of large-scale structures such as galaxy clusters. Cosmological simulations that take these hypothetical explosions into account might better replicate some observed features of the universe that currently remain poorly explained. The chemical legacy of quark novae is another point of intrigue. While supernovae are credited with seeding the universe with many elements beyond hydrogen and helium, the most massive elements, like uranium, thorium, and plutonium, are still shrouded in mystery regarding their exact origins. Some models suggest that the R process, rapid neutron capture process, is responsible for their creation, yet it's not fully clear which environments support it most effectively. Quark novae, by offering a dense bath of neutrons and possibly other exotic particles, could contribute significantly to the galactic inventory of these rare elements. If future spectroscopic studies identify chemical fingerprints unique to quark nova nucleosynthesis, this might explain the presence of certain anomalous isotopes in old stars or even in our own solar system. Moreover, we must consider how quark novae interact with their surrounding environments. In dense stellar clusters, a quark nova's shockwave could trigger cascading effects, compressing nearby gas clouds to form stars, disrupting binary systems, or injecting turbulent energy into the interstellar medium. These local disruptions might then scale up to alter the course of stellar evolution in those regions, adding yet another layer of consequence to an already fascinating event. Similarly, if a quark nova occurred within an accretion disk of a black hole or near a magnetar, the interplay between the explosion and the pre-existing gravitational or magnetic dynamics might yield completely unforeseen phenomena, new types of gamma-ray bursts, gravitational wave spikes, or even jet-like emissions unlike those seen in any supernova or quasar. The detection of such a burst could also expand our understanding of time-domain astronomy. Modern astrophysics increasingly relies on real-time monitoring of transient events, phenomena that appear suddenly and vanish quickly. A confirmed quark nova would be a prize target for space and ground-based observatories across multiple wavelengths. Observatories like the Vera Rubin Observatory, the James Webb Space Telescope, and the European Extremely Large Telescope are poised to monitor the skies in unprecedented detail. A future discovery of a quark nova could serve as a proving ground for these new instruments, validating their predictive models and calibrating their sensitivity to rare but transformative phenomena. As theoretical work pushes forward, we are beginning to construct models of the light curves, graphs that depict how the brightness of an event changes over time, for hypothetical quark novae. These models, when compared against historical data from supernova surveys, could allow astronomers to retroactively identify potential candidates, With machine learning and artificial intelligence becoming integral tools in data analysis, algorithms could soon sift through petabytes of astronomical data, flagging irregular light curves or energy signatures that fit the predicted profile of a quark nova. This approach is already transforming other areas of astrophysics and could soon do the same here. In all this, there is a broader philosophical question that quark novae raise. Where are the limits of collapse, and how many thresholds does nature allow before matter ceases to exist in any recognizable form? Just as white dwarfs collapse into neutron stars and neutron stars might collapse into quark stars, could there be something beyond? Are quark stars stable endpoints, or are they merely stepping stones to even more exotic objects, like preon stars or hypothetical black stars composed of ultradense states of matter yet to be defined? Could there be entire classes of astrophysical bodies we have yet to imagine because we haven't even discovered the processes that create them? This type of thinking aligns with the tradition of discovery that has long characterized human inquiry. We look to the skies not merely to understand what is, but to glimpse what might be. Quark novae, real or not, stretch our understanding of nature's complexity and majesty. They invite us to peer beyond the event horizon of current knowledge and into realms where the rules we thought were fixed begin to bend. Their study is, in many ways, a humbling reminder that the cosmos is not static, but rather a vibrant, dynamic arena of creation, destruction, and transformation. In this cosmic theater, quark novae may be among the most explosive actors, a kind of celestial punctuation mark at the end of a star's long sentence, only to begin a new chapter of unknown grammar and syntax. And in the process, they may offer us the key to long-sought answers about the origin of mass, the fate of collapsing matter, the true structure of space-time, and the hidden connections between the infinitely small and the incomprehensibly large. If confirmed, quark novae could be among the most consequential discoveries in the history of science, not just because of what they are, but because of what they could lead us to uncover next. The implications of quark novae ripple outward not only through astrophysics but through every branch of science that touches the fundamental nature of matter and energy. One area where their influence may be particularly profound is the nascent field of quantum astrophysics, a discipline that seeks to understand how quantum mechanical principles manifest in the largest and most extreme environments in the universe. Quark novae could become one of the primary laboratories for studying such principles on macroscopic scales. The transition from hadronic matter to deca-fine quark matter is, in essence, a quantum phase transition, akin to water freezing or boiling, but driven by the immense gravitational compression of a collapsing star. In such a quantum phase transition, symmetry breaking occurs. This is a fundamental concept in physics, where systems shift from a state of higher symmetry to one of lower symmetry, often releasing energy or altering the governing rules of interaction. The birth of a quark nova may involve a symmetry-breaking process at scales where quantum chromodynamics, QCD, dominates, leading to unexpected particle configurations, new forms of plasma, or even localized violations of expected conservation laws. If any of these phenomena are observed, they might lend credence to emerging theories about vacuum instability, metastable particle states, or the existence of a more fundamental layer of reality beneath quarks themselves, perhaps composed of entities like preons or other hypothetical subquark particles. These possibilities invite renewed interest in the study of the QCD phase diagram, a theoretical representation of how quark matter behaves at various temperatures and densities. While high-energy particle colliders like the LHC and RHIC can probe the high-temperature, low-density region of this diagram, quark novae offer access to the low-temperature, high-density regime, an area that is far more difficult to recreate in a lab. Observations of quark nova light curves, spectra, and remnant structures could be correlated with theoretical predictions on the phase behavior of quark matter, thereby allowing researchers to map the QCD diagram in a new, astrophysical context. Furthermore, the dynamics of the actual phase transition within a quark nova likely produce a wide array of exotic particles and phenomena. One such theoretical product is the strangelet, a hypothetical small clump of strange quark matter that could be ejected from the surface of a forming quark star. Strangelets, if stable, could travel vast distances across space and might be detected on Earth as ultra-high-energy cosmic rays. If discovered, these particles would not only confirm the existence of quark stars and quark novae but would also revolutionize particle physics by proving the stability of strange matter at low temperatures. The search for strangelets has already begun in a number of cosmic ray experiments, as well as in collider experiments where heavy ions are smashed together in hopes of momentarily creating a quark-gluon plasma. To date, no confirmed detection has occurred, but the sensitivities of detection equipment are improving. Should even a single strangelet be discovered, its properties could reveal the equation of state for quark matter, essentially, how it reacts to changes in pressure and density. This in turn would allow us to model the internal structure of quark stars more accurately, refining our predictions about their size, mass, rotational speed, and magnetic field behavior. On the theoretical side, Quark Novae force us to revisit some of the most fundamental concepts in general relativity. Einstein's equations describe how mass and energy curve spacetime, but they don't offer specific guidance on how matter behaves under the pressures found inside neutron stars, let alone the even more extreme conditions required for quark matter. Thus, physicists often rely on equations of state, empirically or theoretically derived models that describe how matter compresses. The problem is, there is still no universally accepted equation of state for ultra-dense matter. The Quark Nova, if validated, would provide the perfect scenario to test competing models, including those that incorporate relativistic corrections, anisotropic pressure conditions, and rotational dynamics. What's more, this has implications for gravitational wave astronomy. The merger of two neutron stars can release gravitational waves, and if such a merger results in a quark nova, the gravitational signal would differ from that of a simple neutron star or black hole merger. These differences, perhaps in the form of a delayed secondary pulse, a longer post-merger oscillation, or an unexpected frequency component, could serve as the smoking gun for a quark nova. With observatories like LIGO, Virgo, and CAGRA already detecting such events, and future detectors like the Einstein Telescope and Cosmic Explorer promising even more sensitivity, the chance of catching a quark nova in the act is higher than ever. In addition to gravitational waves, we must also consider the broader multi-messenger signature of a quark nova. This includes not just light across the electromagnetic spectrum, from gamma rays to radio waves, but also neutrinos. The collapse of a neutron star and subsequent formation of quark matter should release a tremendous burst of neutrinos, as neutrons decay and exotic particle interactions release energy. These neutrinos would be of far higher energy, and in greater numbers than those from typical core collapse supernovae. Facilities like Super Kamiokande, IceCube, and the future Hyper Kamiokande are poised to detect such neutrino bursts. If one were observed in coincidence with a gravitational wave event and a peculiar optical transient, the case for a quark nova would be nearly undeniable. But even if no direct detection occurs soon, the implications of modeling quark novae can still have value in seemingly unrelated fields. For example, the physics of dense plasmas and degenerate matter has parallels in condensed matter systems like superconductors and quark-gluon analogs produced in lab-scale simulations. Likewise, studying how magnetic fields behave under such extreme compression may inform models of solar magnetism, magnetic reconnection in fusion reactors, or the behavior of the early universe's primordial fields. These are all areas where the interdisciplinary insights offered by quark novae could have unexpected, even revolutionary consequences. From a technological standpoint, quark nova research may also drive the development of new computational techniques. Simulating the behavior of quark matter, especially during phase transitions, requires solving equations that span quantum mechanics, general relativity, thermodynamics, and statistical mechanics simultaneously. These challenges are driving innovations in quantum computing, high-performance simulations, and artificial intelligence-based approximations. If these tools succeed, their applications will ripple far beyond astrophysics, potentially transforming how we model complex systems in fields as diverse as finance, climate science, and molecular biology. Moreover, quark novae prompt deeper philosophical inquiries. In contemplating them, we are forced to confront the idea that nature may hide its most powerful transformations in events that are almost invisible, silent, distant, fleeting. Unlike the bright cataclysms of ordinary supernovae, a quark nova might escape our telescopes altogether unless we know precisely what to look for. This makes the universe feel simultaneously more mysterious and more alive, as if it contains not just unknown regions of space, but unknown chapters of physical law waiting to be read. Their theoretical potential stretches the boundaries of imagination itself. Could quark stars, born from Quark Novae, harbor conditions suitable for entirely new forms of chemistry? Could stable forms of quark matter eventually serve as a form of energy storage or propulsion for far future human endeavors? Could their conversion of mass to energy in the core provide insights into harnessing clean, sustainable energy sources on Earth? These questions may sound like science fiction now, but so did gravitational waves, black holes, and quantum entanglement not long ago. Thus, the exploration of Quark Novae is not just about answering questions. It's about finding the right questions to ask. In this pursuit, we are extending the reach of human curiosity into realms no eye has seen, no hand has touched, and no machine has yet recorded. And as we do, we are reminded of a deeper truth, that the universe is not only stranger than we imagine, it is stranger than we can imagine. But with every new theory, every improved telescope, every neutrino burst and gravitational wave, we inch closer to understanding even its most secretive explosions. This march toward understanding Quark Novae inevitably brings us to the profound and interconnected idea of cosmic recycling, an eternal cycle of creation, destruction, and transformation. A quark nova, while representing the death throes of a hyperdense neutron star, could simultaneously be viewed as a new beginning, a metamorphosis from one state of matter to another, more exotic form. The material ejected by such an event, enriched with strange quarks and potentially infused with rare isotopes not seen elsewhere, could seed star-forming regions with elements that go beyond the typical palette of the periodic table. What if some of the material forged in Quark Novae eventually contributed to the formation of planets, or even life itself? This concept urges us to reconsider the narrative of stellar evolution. Typically, we follow a star's life from birth in a nebula to a hydrogen-burning main sequence, then on to its red giant phase, and ultimately to a white dwarf, neutron star, or black hole. But if Quark Novae are real and prevalent, they add another critical chapter to that story. Neutron stars, far from being terminal end states, become gateways to something even more extreme. And perhaps, just perhaps, even quark stars might not be the final destination. Some speculative theories suggest that under still greater pressures, beyond even the formation of deconfined quark matter, matter could collapse into an even denser configuration, potentially forming what has been referred to as a preon star. Though highly speculative and lacking observational support, the mere theoretical pathway from atoms to nuclei to quarks and potentially beyond continues to entice physicists to look deeper. As we reflect on the potential birth of a quark star from a quark nova, it's essential to recognize how different this entity would be from its neutron star progenitor. In a neutron star, the matter is stabilized by neutron degeneracy pressure, with layers of increasingly exotic nuclear pasta configurations as one moves toward the core, spaghetti-like and lasagna-like phases that resist collapse through complex, crystalline nuclear arrangements. But once the transition to quark matter occurs, these configurations break down. The result is a far more homogeneous core dominated by free quarks, likely arranged in a strange quark matter phase, with up, down, and strange quarks in roughly equal proportions. This new matter configuration may exhibit color superconductivity, a theoretical state in which quarks pair up and flow without resistance, a bizarre analog to electrical superconductivity, but one governed by the color charge of quantum chromodynamics rather than electric charge. This color superconducting phase would influence everything from the cooling rate of the quark star to the strength and shape of its magnetic field. It's even theorized that quark stars may emit light and particles in a manner inconsistent with neutron star expectations, possibly producing soft gamma repeaters or anomalous X-ray pulsars that don't conform to known magnetar models. If we can match such emissions with theoretical predictions of color superconducting matter, we would be one step closer to confirming the Quark Nova hypothesis. Additionally, these stars might exhibit solid crusts of normal matter overlaying liquid interiors of deconfined quark plasma. The interactions between this crust and the star's underlying quark material could create unique seismic phenomena. Starquakes, crustal shifts, and resonances could cause sudden glitches in rotational speed, something already observed in certain pulsars. In fact, some astrophysicists suggest that pulsar glitches are not merely surface phenomena but signatures of internal reconfiguration, possibly tied to an evolving quark core or latent heat release during the gradual conversion from nuclear to quark matter. Moreover, if the conversion happens asymmetrically or is uneven throughout the star, it might lead to torques or wobbling in the star's rotation. This would subtly modulate its pulse emissions, providing an indirect signature of internal changes. Advanced timing arrays, like those used in pulsar monitoring projects, might one day catch such signals, giving us the first-time resolved window into a star undergoing an internal phase shift, a rare cosmic transformation hidden behind a veil of exotic matter. We must also consider the implications for cosmology. If quark novae are common in the universe, they could contribute significantly to the reionization of the early universe. Shortly after the Big Bang, the universe entered a period of darkness where photons were trapped by neutral hydrogen. Eventually, something reionized this hydrogen, allowing light to travel freely once again. While early stars and galaxies are considered the primary suspects, exotic high-energy events like quark novae, if they occurred frequently enough in the early universe, might have released sufficient energy and radiation to contribute to this cosmic dawn. Their explosive energy, high neutrino output, and rapid injection of exotic particles would have profoundly altered local regions of space, possibly shaping the large-scale structure of the universe. And what about dark matter? Though currently speculative, there's a growing body of research attempting to link exotic compact objects like quark stars to dark matter. One possibility is that quark stars, or even rogue strangelets from quark nova explosions, could account for a portion of the unseen mass in galaxies. These would be macroscopic dark matter candidates, difficult to detect due to their small size and lack of light emission, but gravitationally influential nonetheless. If quark novae eject large quantities of strange matter into the cosmos, it's not inconceivable that this matter, stabilized over billions of years, has accumulated in galactic halos or interstellar space as a shadowy, unobserved mass population. Moreover, the unique nature of matter created in these explosions could help us better understand why matter dominates over antimatter in the observable universe, a mystery known as baryon asymmetry. The extreme environments of quark novae could momentarily allow interactions that violate charge parity symmetry in subtle ways, creating conditions where matter formation was favored. These interactions, though temporary and localized, may mirror the dynamics of the early universe and help explain why we live in a universe filled with matter rather than one that annihilated itself into pure radiation shortly after its creation. There is also a deeply poetic angle to the study of quark novae. In a cosmos governed by entropy and decay, here lies an engine of rebirth, not of a star into a white dwarf or black hole, but into something perhaps even more extraordinary. In this cosmic chrysalis, a dying neutron star sheds its old shell and emerges as a quark star, humming with the vibrations of newly freed fundamental particles. It is a process that captures the very essence of transformation, one where time, pressure, and mass conspire to tear apart the fabric of matter and reweave it into a new form. And still, so much remains to be explored. Theoretical simulations continue to improve, incorporating the latest refinements in nuclear physics, particle interactions, and general relativity. Each new line of code written for these simulations brings us closer to understanding how the core of a dying neutron star collapses into quark matter, how the phase transition propagates outward, how shock waves and magnetic field lines evolve, and how all of it appears to our instruments, if only we learn how to look. Perhaps the most thrilling realization is that quark novae are not some inaccessible phenomenon at the farthest corners of the cosmos. They may be happening in our own galaxy, quietly unfolding in a region we haven't yet noticed or properly interpreted. Somewhere, right now, a neutron star might be collapsing inward, its core melting into quarks, its crust cracking apart, and an invisible wave of transformation pulsing outward. We might not detect it for years, or even decades, but the signal is on its way, racing across the light years with stories to tell. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. Like the video and subscribe to the channel for more such amazing videos.